to imagine a world ruled by giants, dinosaurs that shook the earth with every step and filled the skies with thunderous roars. For over 160 million years, these magnificent creatures dominated the planet, leaving behind clues that still shape our understanding of life, evolution, and extinction. From the fierce T-Rex to the towering Brachiosaurus, their legacy lives on through fossils and science. Join us on a journey through time as we uncover their habitats, behaviors, and the secrets they left behind. Dinosaurs first emerged during the Triassic period, approximately 230 million years ago. This era marked a significant turning point in Earth's history as the planet was recovering from the devastating Permian-Triassic extinction event that had wiped out nearly 90% of all life on Earth. The earliest dinosaurs were small, agile creatures, quite different from the massive behemoths we often imagine. These pioneering species were bipedal carnivores, walking on two legs and preying on smaller animals. They shared the landscape with other reptiles, including the ancestors of crocodiles and flying pterosaurs. Over millions of years, dinosaurs diversified and adapted to various ecological niches. They evolved into a wide array of forms, from the long-necked sauropods to the armored stegosaurs and the fearsome Tyrannosaurus rex. This diversity allowed dinosaurs to dominate terrestrial ecosystems for over 160 million years. The rise of the dinosaurs coincided with significant changes in Earth's climate and geography. The supercontinent Pangaea was beginning to break apart, creating new habitats and opportunities for these adaptable creatures. This period of change and evolution set the stage for the Age of Dinosaurs, a fascinating chapter in our planet's history that continues to captivate scientists and the public alike. When dinosaurs first appeared on Earth around 230 million years ago, our planet was a dramatically different place. The continents were fused into a single landmass called Pangaea, surrounded by a vast global ocean. This arrangement created unique climate conditions with extreme temperatures and weather patterns unlike anything we experience today. The atmosphere during this time contained significantly higher levels of carbon dioxide compared to our current air composition. This greenhouse effect led to a warmer global climate, with even polar regions experiencing temperate conditions. Lush forests of conifers, ferns, and other primitive plants covered much of the land, providing ample food for the emerging herbivorous dinosaurs. Seasons were more pronounced due to Pangaea's large size, with intense heat in the continental interior during summers and harsh, cold winters. Coastal regions likely experienced more moderate conditions, but were subject to powerful storms fueled by the warm global ocean. This dynamic environment set the stage for dinosaurs to evolve and diversify. As they adapted to various ecological niches, dinosaurs began their reign as the dominant land animals, a position they would hold for over 160 million years until their extinction 66 million years ago. The direct ancestors of dinosaurs were a group of reptiles known as archosaurs. These creatures lived during the Triassic period, about 250 million years ago. Archosaurs were diverse and included the ancestors of crocodiles and pterosaurs, as well as dinosaurs. One crucial group of archosaurs that led to dinosaurs was the dinosauromorphs. These animals shared many features with early dinosaurs, such as an upright posture and adaptations for bipedal locomotion. A well-known example is Largopeton, a small, agile creature that lived around 230 million years ago. Another important ancestor was Largosuchus, a small, lightweight archosaur that possessed several dinosaur-like characteristics. It had elongated leg bones and a hinged ankle joint, which are key features found in early dinosaurs. These adaptations allowed for more efficient movement and likely contributed to the success of their descendants. As we trace the lineage further, we encounter animals like Marsuchus and Silosaurus, which were even closer to true dinosaurs. These creatures exhibited more advanced dinosaur-like features, including a fully upright posture and specialized hip structure. Such adaptations set the stage for the emergence and diversification of dinosaurs that would dominate terrestrial ecosystems for over 160 million years. Early dinosaurs emerged during the Triassic period, evolving from earlier reptilian ancestors. These pioneering dinosaurs exhibited several key differences from their predecessors, marking the beginning of a new era in Earth's history. One significant change was in their posture and leg structure. While their ancestors had sprawling limbs extending from the sides of their bodies, early dinosaurs developed more upright legs positioned directly beneath their bodies. This adaptation allowed for more efficient movement and better support of their body weight, giving them an advantage in speed and endurance. The early dinosaurs also showed changes in their skull structure and teeth. Many developed specialized teeth for different diets, whether for cutting through tough plant material or tearing into flesh. This diversification in feeding strategies allowed them to exploit a wider range of food sources than their predecessors. Another notable difference was in their growth rates and metabolism. Early dinosaurs showed signs of faster growth and higher metabolic rates compared to their cold-blooded ancestors. This shift towards warm-bloodedness, though not yet fully developed, gave them increased activity levels and the ability to thrive in a wider range of environments, setting the stage for their eventual dominance of terrestrial ecosystems for millions of years to come. Early dinosaurs emerged during the Triassic period, about 230 million years ago, and quickly became the dominant land animals. Their success stemmed from several key evolutionary advantages that set them apart from their contemporaries. One significant advantage was their upright posture. Unlike their sprawling reptilian ancestors, dinosaurs developed legs positioned directly under their bodies. This allowed for more efficient movement and better support of their body weight, enabling them to run faster and cover greater distances with less energy expenditure. Dinosaurs also developed a wide range of specialized diets, from plant eating to meat eating, allowing them to exploit various ecological niches. This dietary diversity helped them thrive in different environments and adapt to changing conditions. Additionally, many early dinosaurs were relatively small and agile, which likely helped them evade larger predators and find food more easily. Another crucial advantage was their efficient respiratory system. Dinosaurs evolved air sacs connected to their lungs, similar to modern birds. This system allowed for a continuous flow of oxygen, providing them with more energy for sustained activity. Combined with their improved posture and diverse diets, this respiratory efficiency gave early dinosaurs a significant edge in the competitive prehistoric world. The age of dinosaurs, also known as the Mesozoic era, lasted for an astounding 186 million years. This vast span of time began about 252 million years ago and ended 66 million years ago. During this extensive period, dinosaurs evolved, diversified, and dominated the Earth's ecosystems. Throughout the Mesozoic era, the world underwent significant changes. Continents shifted, climates fluctuated, and various forms of life emerged and disappeared. The dinosaurs themselves evolved from small, agile creatures into an incredible array of species, ranging from the massive long-necked sauropods to the fierce, predatory theropods. This age was not solely about dinosaurs, however. It also saw the rise of many other remarkable creatures, including the first mammals, early birds, and a diverse array of marine reptiles. Plants, too, underwent major evolutionary changes during this time, with flowering plants appearing and spreading across the globe. The age of dinosaurs came to an abrupt end when a massive asteroid struck the Earth, triggering a series of catastrophic events that led to the extinction of most dinosaur species. This event marked the close of the Mesozoic era and ushered in the Age of Mammals, ultimately leading to the world we know today. The earliest known dinosaurs emerged during the Triassic period, approximately 230 million years ago. Among these ancient species were small, agile creatures that laid the foundation for the diverse dinosaur lineages that would follow. One of the earliest known dinosaurs was Eoraptor, a small carnivore that lived in what is now Argentina. This bipedal predator was only about 3 feet long and possessed sharp teeth for catching prey. Another early species was Herrerasaurus, a slightly larger carnivore that inhabited the same region as Eoraptor. In Europe, fossils of Plateosaurus have been discovered, representing one of the first large herbivorous dinosaurs. This long-necked creature reached lengths of up to 26 feet and was an early member of the sauropodomorph group, which would later give rise to the massive long-necked sauropods. Coelophysis, a small theropod dinosaur found in North America, is another well-known early species. These slender, agile predators lived in large groups and provide valuable insights into early dinosaur behavior and social structures. These early dinosaurs set the stage for the incredible diversity and dominance that would characterize the dinosaur reign in the following Jurassic and Cretaceous periods. The supercontinent Pangaea played a crucial role in shaping dinosaur evolution. This massive landmass, which existed from about 290 million to 200 million years ago, provided a continuous landscape for early dinosaurs to roam and diversify. With no oceans to act as barriers, dinosaurs could spread across vast distances, leading to widespread distribution of early species. This continental unity initially promoted similarity among dinosaur populations. However, as Pangaea began to break apart, it set the stage for one of the most significant events in dinosaur evolution. The separation of landmasses created isolated populations, spurring the development of unique adaptations and new species. This process, known as allopatric speciation, was a driving force behind the incredible diversity of dinosaurs that would emerge in the following millions of years. The breakup of Pangaea also led to changes in climate and vegetation across different regions. These environmental shifts forced dinosaurs to adapt to new conditions, further accelerating their evolution. Some areas became more arid, while others turned lush and tropical. This variety of habitats encouraged the evolution of different body types, diets, and survival strategies among dinosaur species. Ultimately, the formation and subsequent fragmentation of Pangaea created a dynamic backdrop for dinosaur evolution. It allowed for initial widespread distribution, followed by isolation and diversification, setting the stage for the remarkable variety of dinosaur species that would dominate the Earth for over 160 million years. The earliest dinosaurs emerged during the Triassic period, approximately 230 million years ago. Our understanding of these ancient creatures comes from a combination of fossil evidence and geological clues preserved in rock layers from that time. One of the most significant pieces of evidence for early dinosaurs comes from the Ischigualasto Formation in Argentina. Here, paleontologists have unearthed fossils of Eoraptor, a small, agile dinosaur that lived around 230 million years ago. Eoraptor is considered one of the earliest known dinosaurs and provides crucial insights into the early evolution of these remarkable animals. Another important discovery is Nyasasaurus, found in Tanzania. Dating back to around 243 million years ago, some scientists argue that Nyasasaurus might be the earliest known dinosaur, though its classification is still debated. These fossils, along with others like Herrerasaurus and Staurikosaurus, help paint a picture of the first dinosaurs as relatively small, bipedal creatures that were just beginning to diversify. Trace fossils, such as footprints and trackways, also provide valuable evidence of early dinosaur activity. These preserved impressions in ancient sediments can reveal information about dinosaur behavior, movement, and distribution, even when body fossils are scarce. By studying both body and trace fossils, scientists continue to refine our understanding of when and how dinosaurs first appeared on Earth. Climate played a crucial role in the rise of dinosaurs during the Triassic period, about 230 million years ago. As the supercontinent Pangaea began to break apart, the Earth's climate underwent significant changes. The once arid interior of Pangaea became more humid and hospitable, creating new environments that were ripe for evolutionary experimentation. These climatic shifts led to increased rainfall and the formation of new river systems and lush forests. This change in vegetation provided ample food sources for herbivorous dinosaurs, allowing them to thrive and diversify. As herbivore populations grew, carnivorous dinosaurs evolved to prey on them, setting the stage for the complex ecosystems of the Mesozoic era. The warmer global temperatures of the Triassic period also favored the cold-blooded reptiles, giving dinosaurs an advantage over their mammal-like reptile competitors. This climate-induced advantage allowed dinosaurs to occupy various ecological niches and spread across the fragmenting supercontinent. Furthermore, the end Triassic extinction event, likely triggered by massive volcanic eruptions and resulting climate change, eliminated many of the dinosaurs' competitors. This mass extinction cleared the way for dinosaurs to become the dominant terrestrial vertebrates for the next 160 million years, shaping the course of evolution on our planet. Scientists have identified and named over 1,000 different species of dinosaurs to date. However, this number continues to grow as paleontologists make new discoveries around the world. It's important to note that this figure represents only a fraction of the total number of dinosaur species that existed during their reign on Earth, which spanned more than 160 million years. The process of discovering and classifying dinosaur species is ongoing and complex. Researchers often work with incomplete fossil records, making it challenging to determine whether certain remains belong to a new species or an already known one. Some estimates suggest that there could have been as many as 10,000 to 15,000 distinct dinosaur species throughout their entire existence. Interestingly, new dinosaur species are being discovered at an increasing rate. In recent years, paleontologists have been finding an average of 30 to 40 new species annually. This surge in discoveries is due to improved technology, more extensive field research, and exploration in previously understudied regions, particularly in South America, Asia, and Africa. These ongoing discoveries not only increase our knowledge about the diversity of dinosaurs, but also provide valuable insights into their evolution, behavior, and the ancient ecosystems they inhabited. Each new species helps paint a more complete picture of life on Earth millions of years ago, constantly reshaping our understanding of prehistoric times. The largest known dinosaur was a colossal sauropod called Argentinosaurus. This enormous herbivore roamed the Earth during the late Cretaceous period, approximately 95 to 66 million years ago. Argentinosaurus was a member of the Titanosaur group, known for their massive size and long necks. Estimating the exact dimensions of Argentinosaurus is challenging due to the incomplete nature of fossil remains. However, based on the fossils discovered, scientists believe this gigantic creature could have reached lengths of up to 30 to 40 meters and may have weighed as much as 80 to 100 metric tons. To put this into perspective, that is about as heavy as 15 adult African elephants combined. The sheer size of Argentinosaurus raises fascinating questions about its lifestyle and the ecosystem it inhabited. Its immense body would have required vast amounts of plant material to sustain itself, likely consuming hundreds of kilograms of vegetation daily. The dinosaur's long neck would have allowed it to reach high into the tree canopy, accessing food sources that were out of reach for smaller herbivores. Despite its enormous size, Argentinosaurus was not invulnerable to predators. Large carnivorous dinosaurs of the time, such as Giganotosaurus, might have hunted Argentinosaurus, especially targeting younger or weaker individuals. The discovery of such massive creatures continues to captivate our imagination and deepens our understanding of the incredible diversity of life that once inhabited our planet. The smallest known dinosaur was a fascinating creature called Compsognathus. This diminutive dinosaur lived during the late Jurassic period, approximately 150 million years ago. Compsognathus was roughly the size of a chicken, measuring only about 1 meter in length from its snout to the tip of its tail. It weighed a mere 2 to 3 kilograms, making it one of the lightest dinosaurs ever discovered. Despite its small size, Compsognathus was a formidable predator. It had sharp teeth and agile limbs, allowing it to chase down and capture small prey such as lizards and insects. Fossil evidence suggests that Compsognathus was a swift runner, using its speed and agility to navigate the prehistoric landscapes of what is now Europe. The discovery of Compsognathus challenged many preconceptions about dinosaurs. It demonstrated that not all dinosaurs were enormous, lumbering beasts, but that the group included a diverse range of sizes and body types. This tiny dinosaur played a crucial role in helping scientists understand the evolutionary relationships between dinosaurs and birds, as it shared several anatomical features with early avian species. Dinosaurs roamed the Earth for over 160 million years, evolving into a diverse array of species across different land masses. During the Mesozoic era, when dinosaurs thrived, the continents were arranged differently than they are today, forming the supercontinent Pangaea before gradually separating. In North America, some of the most iconic dinosaurs evolved, including the massive Tyrannosaurus rex and the three-horned Triceratops. This continent was also home to a variety of hadrosaurs, or duck-billed dinosaurs, which were herbivores with complex tooth batteries for grinding plant material. South America hosted unique species like the Giganotosaurus, a carnivore that rivaled Tyrannosaurus rex in size. This continent was also home to some of the largest known dinosaurs, including the long-necked sauropod Argentinosaurus. The isolation of South America during parts of the Cretaceous period led to the evolution of distinctive dinosaur lineages not found elsewhere. Africa and Europe, which were closer together during the Age of Dinosaurs, shared some similar species. However, Africa was home to unusual predators like Spinosaurus, a semi-aquatic theropod with a sail-like structure on its back. In Europe, smaller carnivores like baryonyx and herbivores such as iguanodon were common. Asia, particularly China and Mongolia, has yielded fossils of feathered dinosaurs, providing crucial evidence for the evolutionary link between dinosaurs and birds. The world of dinosaurs was filled with an astonishing array of creatures, many of which would seem utterly alien to us today. One prime example is the Therizinosaurus, a massive theropod with enormous scythe-like claws that could grow up to 3 feet long. Despite its fearsome appearance, this gentle giant was actually a plant-eater, using its claws to pull down branches and defend itself. Another peculiar dinosaur was the Deinocheirus, which sported a duck-like bill, a humped back, and long arms ending in huge claws. This odd combination of features puzzled scientists for decades until more complete fossils were discovered. The Stegosaurus, while more familiar, was no less strange with its tiny head, rows of plates along its back, and spiked tail. The Parasaurolophus stands out with its long, curved head crest, which may have been used for visual display or to produce loud, resonating calls. Similarly bizarre was the Spinosaurus, now believed to have been semi-aquatic, with its massive sail-like structure on its back and a crocodile-like snout filled with conical teeth. These examples barely scratch the surface of the weird and wonderful world of dinosaurs. From the horned face of Triceratops to the thick-headed Pachycephalosaurus, the Mesozoic era was home to a diverse cast of characters that continue to captivate our imagination and fuel scientific inquiry. Dinosaurs were remarkably adaptable creatures, thriving in a wide range of environments across the globe for over 160 million years. Their success was largely due to their ability to evolve and adapt to changing conditions and diverse habitats. In arid regions, some dinosaurs developed specialized features to conserve water. For instance, certain sauropods had long necks that allowed them to reach vegetation high in trees, reducing the need to move frequently in search of food and water. Some dinosaurs in hot climates may have had blood vessels close to their skin surface, similar to modern elephants, helping them regulate body temperature more efficiently. Dinosaurs in colder environments developed different adaptations. Some species, like the Troodon, had larger brains relative to their body size, potentially allowing for more complex behaviors to survive in challenging conditions. Evidence suggests that some dinosaurs living in polar regions may have been warm-blooded, or have had some form of insulation, such as primitive feathers or fur-like coverings to maintain body heat. Coastal and semi-aquatic dinosaurs, such as the Spinosaurus, evolved features like webbed feet and crocodile-like snouts, perfectly suited for catching fish and navigating watery habitats. These adaptations showcase the incredible diversity and resilience of dinosaurs, highlighting their ability to thrive in almost every terrestrial environment on prehistoric Earth. Dinosaurs roamed the Earth for over 160 million years, evolving into a diverse array of species. Among the most common were the Tyrannosaurus rex, a fearsome predator that lived during the late Cretaceous period. This massive carnivore stood up to 20 feet tall and had powerful jaws filled with serrated teeth. Another prevalent dinosaur was the Triceratops, easily recognized by its 3 horns and large frill. These herbivores were about 30 feet long and lived alongside Tyrannosaurus rex. Stegosaurus was also quite common, known for the distinctive plates along its back and the spikes on its tail. Velociraptor, made famous by popular culture, was actually much smaller than often depicted, about the size of a turkey. These quick, intelligent predators lived in what is now Mongolia. Brachiosaurus, a massive long-necked herbivore, was one of the largest animals to ever walk on land, reaching heights of up to 50 feet. Lastly, the Ankylosaurus was a common armored dinosaur, covered in bony plates and wielding a club-like tail. These plant-eaters used their natural armor and formidable tail weapon to defend against predators. Each of these species played a crucial role in their respective ecosystems, shaping the prehistoric world for millions of years. Dinosaur diversity underwent significant changes throughout their reign on Earth, spanning approximately 165 million years. During the Triassic period, dinosaurs first emerged and gradually diversified. They began as small bipedal creatures and slowly evolved into a wider variety of forms. The Jurassic period saw an explosion in dinosaur diversity. This era witnessed the rise of massive sauropods, swift theropods, and the first avian dinosaurs. Iconic species like Stegosaurus and Allosaurus roamed the landscape, showcasing the increasing variety of dinosaur body plans and ecological niches. The Cretaceous period marked the peak of dinosaur diversity. Herbivorous groups like hadrosaurs and ceratopsians flourished, while carnivorous theropods, including the famous Tyrannosaurus rex, dominated as apex predators. This era also saw the continued evolution of avian dinosaurs, setting the stage for modern birds. However, dinosaur diversity faced a catastrophic decline at the end of the Cretaceous. A massive asteroid impact, combined with ongoing environmental changes, led to the extinction of most dinosaur species. This event marked the end of the dinosaurs' dominance, leaving only their avian descendants to carry their legacy into the modern era. Dinosaurs flourished on Earth for over 160 million years, evolving into a remarkable array of species. This incredible diversity was driven by several key factors. Foremost among these was the long period of relative environmental stability during the Mesozoic era, which allowed dinosaurs ample time to adapt and specialize. The breakup of the supercontinent Pangaea played a crucial role in dinosaur diversification. As landmasses drifted apart, dinosaur populations became isolated, leading to the evolution of unique species adapted to their specific environments. This geographical separation created natural laboratories for evolution, resulting in a wide variety of dinosaur forms across different continents. Climate change throughout the Mesozoic also contributed to dinosaur diversity. Fluctuations in temperature and humidity led to the development of new ecosystems, prompting dinosaurs to evolve specialized features to exploit these emerging niches. For instance, some dinosaurs developed long necks to reach high vegetation, while others evolved armor plating for defense. Competition between species was another driving force behind dinosaur diversity. As different dinosaur lineages vied for resources, they evolved distinct adaptations to gain advantages over their rivals. This evolutionary arms race resulted in an astounding variety of body shapes, sizes, and specialized features, from the massive sauropods to the agile, feathered theropods that would eventually give rise to birds, offering a vibrant window into the prehistoric world. These ancient color molecules, preserved for millions of years, provide crucial evidence about the hues and patterns that adorned dinosaur bodies, feathers, and scales. Melanosomes, tiny structures containing melanin pigments, have been discovered in exceptionally well-preserved fossils. By analyzing the shape and arrangement of these melanosomes, scientists can determine the colors of dinosaur feathers and skin. This technique has revealed that some dinosaurs sported vibrant patterns, including stripes and spots, challenging the long-held notion of drab, monochromatic creatures. One remarkable example is Sinosauropteryx, a small theropod dinosaur from China. Fossil pigment analysis showed it had a reddish-brown and white striped tail, suggesting complex color patterns were present even in early feathered dinosaurs. Another fascinating case is Psittacosaurus, whose countershading camouflage pattern was revealed through careful study of preserved pigments. These discoveries not only paint a more accurate picture of dinosaur appearance, but also provide insights into their behavior and ecology. Colorful plumage might have played a role in mate selection or species recognition, while camouflage patterns could indicate predator avoidance strategies. As techniques for analyzing fossil pigments continue to advance, we can expect even more surprising revelations about the vibrant world of dinosaurs. Recent advances in paleontology have revolutionized our understanding of dinosaur coloration, shedding new light on their behavior and ecology. By analyzing fossilized pigment cells called melanosomes, scientists can now determine the colors and patterns of some dinosaur species with remarkable accuracy. This breakthrough has far-reaching implications for our comprehension of dinosaur behavior, social interactions, and survival strategies. The discovery of vibrant colors and intricate patterns in dinosaur feathers and scales challenges the long-held notion of drab, reptilian creatures. We now know that many dinosaurs sported bright hues and complex markings, suggesting they used visual displays for communication, courtship, and territorial defense. This insight into their appearance allows us to draw parallels with modern birds and their elaborate mating rituals, hinting at similar behaviors in their dinosaur ancestors. Coloration also plays a crucial role in camouflage and predator-prey relationships. Understanding the color patterns of both predatory and herbivorous dinosaurs helps paleontologists reconstruct ancient ecosystems and food chains with greater accuracy. For instance, the discovery of countershading in some dinosaur species indicates they needed to blend into their environment, either to avoid predators or to ambush prey. Furthermore, the presence of certain colors and patterns can provide clues about dinosaur habitats and lifestyles. Bright, contrasting colors might indicate a dinosaur lived in dense forests where visual signals were necessary for communication, while more muted tones could suggest open plains dwelling. By piecing together these colorful clues, scientists are painting a more vivid and dynamic picture of the Mesozoic world, transforming our understanding of dinosaur behavior and ecology. Many dinosaurs sported feathers, a revelation that has transformed our understanding of these ancient creatures. The most famous feathered dinosaurs belong to the theropod group, which includes the ancestors of modern birds. Tyrannosaurus rex, the iconic predator, likely had feathers covering parts of its body, especially when young. Velociraptor, made famous by popular culture, was actually covered in feathers from head to tail, resembling a flightless bird more than the scaly monster often depicted. Smaller theropods like Sinosauropteryx and Dilongparadoxus were completely covered in primitive feathers, providing insulation and possibly serving display purposes. The four-winged Microraptor had complex feathers on both its arms and legs, suggesting it could glide between trees. Even some larger dinosaurs outside the theropod group, such as Psittacosaurus, a relative of Triceratops, had bristle-like feathers along its tail. Recent discoveries have shown that feathers were not limited to carnivorous dinosaurs. Some plant-eating ornithischian dinosaurs, like Culindrodromeus zabicalicus, also had feather-like structures. This suggests that feathers may have been a feature of the common ancestor of all dinosaurs, evolving for insulation before being adapted for flight in some lineages. The presence of feathers in dinosaurs provides a direct link to modern birds, supporting the theory that birds are living dinosaurs. As we continue to unearth new fossils and develop better imaging techniques, our understanding of feathered dinosaurs continues to evolve, painting a more colorful and diverse picture of the prehistoric world. Feathers first appeared in dinosaurs during the late Jurassic period, approximately 150 million years ago. This groundbreaking development marked a significant milestone in the evolution of these ancient creatures, setting the stage for the eventual emergence of birds. The earliest known feathered dinosaur, Archaeopteryx, lived during this time and provides crucial evidence for the link between dinosaurs and modern birds. However, recent fossil discoveries suggest that simpler, hair-like feathers might have evolved even earlier, possibly in the Middle Jurassic period, around 170 million years ago. These early feathers were likely used for insulation and display rather than flight. As dinosaurs continued to evolve, feathers became more complex and diverse, serving various functions such as temperature regulation, camouflage, and eventually powered flight in some lineages. The evolution of feathers in dinosaurs represents a fascinating example of how a seemingly simple adaptation can lead to profound changes in an organism's lifestyle and capabilities, ultimately resulting in the diverse array of bird species we see today. Dinosaur feathers initially evolved for purposes other than flight, serving crucial roles in the lives of these ancient creatures. Insulation was likely one of the primary functions, helping dinosaurs regulate their body temperature. This thermal regulation was particularly important for smaller dinosaur species and juveniles, allowing them to maintain warmth in cooler environments and cool off in hotter climates. Another significant purpose of feathers was display and communication. Many dinosaur species developed colorful and elaborate feather patterns, which played a role in attracting mates, intimidating rivals, and signaling to other members of their species. These visual displays could convey information about age, health, and social status within dinosaur communities. Feathers also provided camouflage for some dinosaur species, helping them blend into their surroundings. This adaptation was particularly useful for smaller predatory dinosaurs, allowing them to hide from larger predators or sneak up on prey. Additionally, feathers offered a degree of protection, acting as a barrier against minor injuries and environmental hazards. The evolution of feathers for flight came later, building upon these earlier adaptations. As certain dinosaur lineages evolved into birds, feathers gradually developed the aerodynamic properties necessary for powered flight. This transformation highlights how structures that originally evolved for one purpose can be repurposed through natural selection to serve entirely new functions. Feathers evolved over millions of years, gradually transforming from simple structures into the complex flight-enabling marvels we see in birds today. This process began with dinosaurs, the ancestors of modern birds, which initially developed simple, hair-like feathers for insulation. These early feathers underwent significant changes as they adapted to serve new purposes. They became larger and more complex, developing a central shaft with barbs branching off to create a flat surface. This structure provided better insulation and eventually proved useful for display and courtship rituals. The next crucial step was the evolution of asymmetrical feathers. These feathers had a stronger leading edge, which allowed for better airflow and increased lift. This development was a key factor in the transition from gliding to active flight. Simultaneously, the feathers became lighter yet stronger, thanks to a hollow central shaft and interlocking barbules that connected the barbs. As dinosaurs evolved into early birds, their feathers continued to refine. The arrangement of feathers on the body became more aerodynamic, and different types of feathers evolved to serve specific functions in flight. This long process of adaptation ultimately resulted in the highly efficient flight feathers we observe in modern birds, capable of generating lift, reducing drag, and enabling precise aerial maneuvers. Not all theropod dinosaurs were feathered, but evidence suggests that many of them had feathers or feather-like structures. Paleontologists have discovered fossilized feathers or feather impressions on numerous theropod species, ranging from small, bird-like dinosaurs to larger predators. The presence of feathers in theropods varied widely across different groups and time periods. Some early theropods likely had simple, hair-like structures called protofeathers, while later species developed more complex feathers similar to those of modern birds. Certain theropod groups, such as the maniraptors, which include velociraptors and the ancestors of modern birds, were extensively feathered. However, some large theropods, like Tyrannosaurus rex, may have had only patches of feathers or scales covering most of their bodies. The exact distribution of feathers among theropods is still a subject of ongoing research and debate among paleontologists. As new fossils are discovered and analyzed, our understanding of feathered dinosaurs continues to evolve, providing a more complete picture of these fascinating prehistoric creatures and their connection to modern birds. Recent scientific discoveries have revealed that feathers were not exclusive to carnivorous dinosaurs or early birds. Several herbivorous dinosaur species indeed possessed feathers, challenging our previous understanding of dinosaur appearance and evolution. One notable example is the Colindodromeus zabicalicus, a small herbivorous dinosaur that lived approximately 160 million years ago. Fossil evidence shows that this plant eater had scales on its tail and lower legs, but also displayed feather-like structures on other parts of its body. This finding suggests that feathers might have been more widespread among dinosaurs than previously thought. Another fascinating case is the Psittacosaurus, a beaked herbivorous dinosaur related to Triceratops. While not covered in feathers, it had quill-like structures on its tail, which some scientists believe could be a precursor to feathers. These structures might have served purposes such as display, communication, or temperature regulation. These discoveries are reshaping our image of dinosaurs and providing valuable insights into the evolution of feathers. They suggest that feathers may have originally evolved for purposes other than flight, such as insulation or display, before being co-opted for aerial locomotion in later species. This underscores the complex and diverse nature of dinosaur evolution, blurring the lines between what we once considered distinct groups of these ancient creatures. Fossilized feathers and modern bird feathers share fundamental structures, but time and the fossilization process create distinct differences. Fossilized feathers are typically preserved as impressions in rock, often appearing as dark streaks or faint outlines. These ancient imprints lack the vibrant colors and soft textures of living feathers, instead offering a monochromatic glimpse into the past. The fossilization process can alter the feather's original shape and size. Compression over millions of years may flatten the feather, distorting its three-dimensional structure. This flattening can make it challenging for paleontologists to determine the exact species or even the specific type of feather they're examining. Despite these changes, fossilized feathers still retain crucial details. Scientists can often identify the feather's raches or central shaft, as well as the barbs branching off it. In some extraordinarily well-preserved specimens, even the microscopic hooks that hold the barbs together, called barbules, are visible. These minute structures provide valuable insights into the evolution of feathers and their functions. One significant difference lies in the preservation of pigments. While modern feathers display a wide array of colors, most pigments break down over time. However, recent advancements in technology have allowed researchers to detect traces of melanin, the pigment responsible for black, gray, and brown colors in some fossilized feathers. This discovery has opened new avenues for understanding the appearance of ancient birds and feathered dinosaurs, bridging the gap between the fossilized past and the living present. The distribution of feathers on dinosaur fossils provides crucial insights into their evolution and the emergence of birds. Paleontologists have discovered feather impressions on a wide range of dinosaur species, revealing a complex and fascinating story of adaptation and diversification. Feathers were not exclusive to flying dinosaurs. Many ground-dwelling theropods, including some tyrannosaurs and velociraptors, had feather-like structures. This widespread presence suggests that feathers initially evolved for purposes other than flight, such as insulation or display. The variety of feather types found on different dinosaur species indicates a gradual development from simple, hair-like structures to the complex flight feathers seen in modern birds. The distribution of feathers also helps scientists understand the relationships between different dinosaur groups. Species with similar feather patterns are often more closely related, allowing researchers to refine the dinosaur family tree. Furthermore, the presence of feathers on both bird-like and non-avian dinosaurs strengthens the evidence for the evolutionary link between dinosaurs and modern birds. By studying feather distribution, scientists can reconstruct the appearance and behavior of extinct dinosaurs more accurately. This knowledge enhances our understanding of dinosaur ecology, social interactions, and the evolutionary pressures that ultimately led to the development of powered flight in birds. The study of feather distribution continues to reshape our view of dinosaurs, transforming them from scaly reptiles to diverse, often feathered creatures that dominated the Earth for millions of years. Feathers played a crucial role in dinosaur thermoregulation, revolutionizing how these ancient creatures regulated their body temperature. Initially evolving for insulation, feathers provided dinosaurs with a versatile tool to adapt to various climates and environments. The insulating properties of feathers helped dinosaurs retain heat, allowing them to maintain warmer body temperatures even in cooler conditions. This was particularly important for smaller dinosaur species, which could have lost heat quickly due to their high surface area to volume ratio. Feathers acted as a barrier, trapping a layer of warm air close to the skin and reducing heat loss to the environment. Conversely, feathers also aided in cooling. By fluffing or flattening their feathers, dinosaurs could adjust how much heat they retained or released. This flexibility in thermoregulation gave feathered dinosaurs a significant advantage, enabling them to remain active in a wider range of temperatures compared to their non-feathered counterparts. The evolution of feathers for thermoregulation likely contributed to the success and diversity of dinosaur species. It allowed them to expand into new habitats and potentially maintain higher metabolic rates, leading to more active lifestyles. This adaptation ultimately set the stage for the evolution of powered flight in some dinosaur lineages, culminating in the birds we see today. Dinosaur feathers were indeed diverse, varying significantly across different species. Recent paleontological discoveries have revealed a wide array of feather types, each adapted to specific functions and environments. Some dinosaurs had simple, hair-like structures called proto-feathers, which likely served as insulation. These primitive feathers were found in many theropod dinosaurs, including some early tyrannosaurs. Other dinosaurs evolved more complex feather structures. Some species possessed downy feathers, similar to those found on modern bird chicks, which provided warmth and possibly played a role in visual displays. Certain theropod dinosaurs, particularly those closely related to birds, developed pennaceous feathers with a central shaft and barbs, resembling the flight feathers of modern birds. Interestingly, not all feathered dinosaurs could fly. Many ground-dwelling dinosaurs had feathers for insulation, camouflage, or display purposes. For example, some large theropods like Utyrannus, a relative of Tyrannosaurus rex, had a coat of primitive feathers despite their massive size. This suggests that feathers initially evolved for purposes other than flight and were later co-opted for aerial locomotion in some lineages. The diversity of dinosaur feathers extended to their colors and patterns as well. Fossilized pigment cells have allowed scientists to reconstruct the colors of some dinosaur feathers, revealing a palette ranging from muted browns and grays to iridescent blues and greens. This variety in feather types, structures, and colors paints a picture of dinosaurs as diverse and colorful creatures, far from the drab, scaly images that dominated popular imagination for many years. The question of whether dinosaurs were warm-blooded or cold-blooded has intrigued scientists for decades. Recent evidence suggests that the answer is not as simple as one or the other. Many dinosaurs likely had a metabolism that fell somewhere between that of modern reptiles and mammals. Studies of dinosaur bones have revealed growth patterns similar to those of warm-blooded animals. This indicates that dinosaurs grew quickly and maintained high activity levels, which is characteristic of warm-blooded creatures. However, some larger dinosaurs may have had a metabolism more like that of modern turtles or crocodiles, able to maintain a steady body temperature due to their massive size rather than internal processes. Certain dinosaur groups, particularly the theropods, which include the ancestors of modern birds, show strong evidence of being fully warm-blooded. They had features like hollow bones and possibly even feathers, which are typically associated with warm-blooded animals. On the other hand, some herbivorous dinosaurs might have had a metabolism closer to that of cold-blooded animals. This complex picture suggests that dinosaurs exhibited a range of metabolic strategies. As they evolved over millions of years, different dinosaur species likely developed varied approaches to regulating their body temperature and energy use. This diversity in metabolic function may have contributed to the success and dominance of dinosaurs in prehistoric ecosystems. The warm-blooded dinosaur theory has gained substantial support from various lines of evidence gathered over the years. One key piece of evidence comes from studying dinosaur bones at the microscopic level. These studies reveal growth patterns similar to those found in modern warm-blooded animals, suggesting dinosaurs grew quickly and maintained high metabolic rates throughout their lives. Fossil discoveries have also provided crucial insights. Some dinosaur fossils show preserved feathers, which are typically associated with warm-blooded animals and serve as insulation. Additionally, dinosaur fossils have been found in polar regions, indicating these creatures could survive in cold climates, a trait more common in warm-blooded animals. The posture and limb structure of many dinosaurs also support the warm-blooded theory. Upright postures and legs positioned directly under the body are more energy efficient and typical of warm-blooded animals. This arrangement allows for sustained activity levels that cold-blooded animals generally cannot maintain. Chemical analysis of dinosaur eggshells has revealed isotope ratios consistent with warm-blooded metabolisms. Furthermore, studies of dinosaur nasal passages suggest they had the ability to warm inhaled air and conserve water vapor, features commonly found in warm-blooded animals. These multiple lines of evidence, while not conclusive, strongly support the idea that many dinosaurs were indeed warm-blooded. The warm-blooded debate centers on the metabolic differences between endothermic and ectothermic animals, with growth rates playing a crucial role in our understanding. Endothermic animals, such as mammals and birds, maintain a constant internal body temperature regardless of their environment. This ability comes at a high energy cost, requiring these animals to consume more food to fuel their metabolism. Ectothermic animals, like reptiles and amphibians, rely on external sources to regulate their body temperature. This energy-efficient approach allows them to survive on less food, but it also affects their growth rates. Scientists have observed that endothermic animals generally grow faster than their ectothermic counterparts, especially in cooler environments where ectotherms struggle to maintain optimal body temperatures for growth. However, the relationship between growth rates and metabolic strategies is not always straightforward. Some ectothermic dinosaurs, for instance, exhibited growth rates comparable to modern endotherms, challenging our assumptions about the link between metabolism and growth. This has led researchers to propose that some dinosaurs may have had intermediate metabolic strategies, blurring the line between warm and cold-blooded animals. These findings have sparked new questions about the evolution of endothermy and its impact on animal physiology and behavior. By studying growth rates in both living and extinct species, scientists continue to refine our understanding of the complex interplay between metabolism, environment, and animal development. Dinosaurs, those remarkable creatures that dominated Earth for over 160 million years, exhibited a fascinating range of metabolic rates across different groups. Recent studies have shed light on this intriguing aspect of dinosaur physiology, revealing a complex picture that challenges our previous understanding. Theropods, the group that includes the famous Tyrannosaurus rex and modern birds, appear to have had high metabolic rates similar to those of warm-blooded animals today. This aligns with their active predatory lifestyles and the eventual evolution of flight in their avian descendants. Evidence from bone structure and growth rates supports this view, suggesting that theropods were capable of sustained activity and rapid growth. In contrast, long-necked sauropods like Brachiosaurus and Diplodocus likely had lower metabolic rates, more akin to those of modern reptiles but not quite as low. Their massive size and plant-based diets may have necessitated a different energy management strategy. This metabolic profile would have allowed them to efficiently process large amounts of vegetation while maintaining their enormous body mass. Ornithischians, which include duck-billed hadrosaurs and armored dinosaurs like Stegosaurus, seem to have occupied a middle ground. Their metabolic rates were probably higher than those of modern reptiles, but not as high as those of theropods. This intermediate metabolism might have provided a balance between energy needs for defense mechanisms, such as elaborate horns or armor, and the ability to efficiently process plant material. Dinosaur bone structure provides crucial insights into their metabolism, offering a window into the lives of these ancient creatures. Recent studies of dinosaur fossils have revealed intricate details about their bone tissue, particularly the presence of lines of arrested growth and the density of blood vessels within the bone. Many dinosaur species show rapid bone growth in their early years, similar to modern birds and mammals. This fast growth requires a high metabolic rate to fuel the rapid formation of new bone tissue. The presence of numerous blood vessels in dinosaur bones further supports the idea of an active metabolism, as these vessels would have supplied the bones with the nutrients needed for swift growth. However, not all dinosaurs exhibit the same bone structure. Some species, particularly larger ones, show signs of slowing growth as they aged, indicated by closely spaced growth rings in their bones. This suggests that their metabolism might have changed over their lifespan, possibly becoming more like that of modern reptiles as they reached adulthood. The relationship between bone structure and metabolism in dinosaurs continues to be a subject of intense research. By comparing dinosaur bones to those of modern animals, scientists are piecing together a more complete picture of how these fascinating creatures lived and functioned millions of years ago. Dinosaur breathing systems offer fascinating insights into their metabolism and activity levels. Recent research on dinosaur fossils has revealed intricate respiratory structures that resemble those found in modern birds. These structures, known as air sacs, allowed for a highly efficient method of breathing called flow-through ventilation. In this system, air moves through the lungs in one direction, enabling a continuous supply of oxygen-rich air. This is markedly different from the in-and-out breathing patterns seen in mammals. The presence of these air sacs suggests that many dinosaurs, particularly theropods and sauropods, had high metabolic rates similar to those of birds today. This efficient respiratory system would have provided dinosaurs with the oxygen needed to support an active, warm-blooded lifestyle. It allowed them to engage in energy-intensive activities such as hunting, long-distance migration, and rapid growth. The ability to process oxygen more effectively also implies that dinosaurs could have thrived in environments with lower oxygen levels than previously thought. Furthermore, the presence of air sacs in dinosaur bones made their skeletons lighter, potentially enabling larger body sizes and more agile movement. This respiratory adaptation, combined with other anatomical features, paints a picture of dinosaurs as dynamic, energetic creatures rather than the slow, lumbering beasts once imagined. These findings continue to reshape our understanding of dinosaur physiology and behavior, providing a window into the active lives of these ancient reptiles. The warm-blooded nature of dinosaurs likely had a profound impact on their behavior and lifestyle. Unlike their cold-blooded reptilian cousins, warm-blooded dinosaurs could maintain a constant body temperature, allowing them to remain active in various climates and at different times of day. This ability potentially enabled dinosaurs to be more energetic and aggressive predators, or more vigilant and quick-reacting prey. Being warm-blooded would have required dinosaurs to consume more food to fuel their higher metabolic rates. This need for increased sustenance might have driven them to develop more complex hunting strategies or to forage over larger territories. It could also explain the evolution of herding behaviors in some species, as group foraging would have been more efficient. The constant body temperature of warm-blooded dinosaurs might have allowed for more complex social behaviors. They could have engaged in activities like group hunting, elaborate mating rituals, or extended parental care, which are more commonly associated with warm-blooded animals today. This temperature regulation also might have enabled dinosaurs to inhabit a wider range of environments, from tropical regions to polar areas. Moreover, being warm-blooded could have influenced dinosaur growth rates and life cycles. Many scientists believe that this characteristic allowed dinosaurs to grow faster than cold-blooded reptiles, potentially reaching sexual maturity earlier and having shorter generation times. This rapid growth and development might have contributed to the incredible diversity and adaptability of dinosaurs throughout their long reign on Earth. Dinosaurs have long captivated our imagination, but their true nature continues to spark scientific debate. When it comes to the question of cold-blooded dinosaurs, the answer is not as straightforward as we once thought. Traditionally, dinosaurs were believed to be cold-blooded or ectothermic, like modern reptiles. This view stemmed from their reptilian features and the assumption that they were simply scaled-up versions of today's lizards and crocodiles. However, recent research has challenged this notion, suggesting a more complex picture of dinosaur physiology. Evidence from bone structure, growth rates, and even chemical analysis of fossils indicates that many dinosaurs were likely warm-blooded or endothermic, similar to modern birds and mammals. This would have allowed them to maintain high activity levels and thrive in various climates. Some scientists propose that dinosaurs might have had an intermediate metabolism, neither fully cold-blooded nor warm-blooded, but somewhere in between. While the debate continues, current evidence suggests that truly cold-blooded dinosaurs were likely rare if they existed at all. Most dinosaurs probably had some degree of internal temperature regulation, allowing them to dominate Earth's ecosystems for over 160 million years. The warm-blooded debate surrounding dinosaurs has significantly reshaped our understanding of their activity levels and overall behavior. For decades, scientists assumed dinosaurs were cold-blooded like modern reptiles, implying they were sluggish and required external heat sources to function. However, recent evidence suggests many dinosaurs may have been warm-blooded, similar to modern birds and mammals. This shift in perspective has led researchers to reconsider dinosaur activity levels. Warm-blooded animals can maintain a constant internal temperature, allowing for sustained periods of activity regardless of external conditions. If dinosaurs were indeed warm-blooded, it would mean they could have been far more active and agile than previously thought, capable of pursuing prey or evading predators with greater stamina and speed. The warm-blooded hypothesis also impacts our understanding of dinosaur metabolism and growth rates. Warm-blooded animals typically have higher metabolic rates, requiring more food to sustain their energy needs. This could explain the massive size some dinosaur species achieved and their rapid growth patterns observed in fossil records. Furthermore, the possibility of warm-blooded dinosaurs has implications for their behavior and social structures. It suggests they might have engaged in more complex social interactions, potentially including group hunting, extended parental care, and sophisticated mating rituals. These considerations continue to fuel ongoing research and debate in paleontology, constantly refining our image of how dinosaurs lived and behaved millions of years ago. Birds are the closest living relatives of dinosaurs and serve as excellent metabolic analogues for their extinct ancestors. Modern birds, especially large flightless species like ostriches and emus, provide valuable insights into dinosaur metabolism. These birds possess high metabolic rates and maintain warm body temperatures, characteristics that scientists believe many dinosaurs shared. Crocodiles and alligators, while more distantly related, also offer important clues about dinosaur metabolism. These reptiles, which have remained relatively unchanged for millions of years, represent a more conservative metabolic model. Some researchers suggest that certain dinosaur groups might have had metabolic rates intermediate between modern birds and crocodiles. Interestingly, large mammals like elephants can also serve as metabolic analogues for the largest dinosaurs. Both groups faced similar challenges in thermoregulation due to their massive size. By studying how elephants manage their body temperature and energy needs, scientists can make informed inferences about the metabolic processes of giant sauropods and other massive dinosaurs. Recent research combining evidence from growth rates, bone structure, and oxygen isotope analysis supports the idea that many dinosaurs were endothermic or warm-blooded, like modern birds and mammals. This makes birds and mammals particularly valuable as metabolic analogues, helping us better understand how dinosaurs lived, grew, and thrived in their ancient environments. Dinosaurs likely produced a wide range of vocalizations, though the exact nature of these sounds remains a subject of scientific speculation. While we cannot hear their calls directly, paleontologists have made educated guesses based on fossil evidence and comparisons with modern animals. Some dinosaurs, particularly hadrosaurs or duck-billed dinosaurs, had elaborate hollow crests that might have functioned as resonance chambers. These structures suggest they could produce low-frequency booming calls, similar to the trumpeting of elephants or the deep bellows of large crocodiles. Smaller dinosaurs might have chirped or whistled, not unlike modern birds, which are their direct descendants. Tyrannosaurus rex and other large predators possibly roared or produced deep, guttural growls, comparable to those of lions or alligators. However, recent studies indicate they might have produced closed-mouth vocalizations, more akin to cooing or booming sounds. It is important to note that soft tissues like vocal cords rarely fossilize, making it challenging to determine precisely how dinosaurs sounded. As research continues, our understanding of dinosaur vocalizations may evolve, potentially revealing a prehistoric soundscape far more diverse and complex than we currently imagine. Scientists employ several innovative methods to study potential dinosaur vocalizations, despite the obvious challenge of never having heard an actual dinosaur call. One approach involves analyzing the structure of fossilized dinosaur throats and vocal organs. By examining the shape and size of these structures, researchers can make educated guesses about the types of sounds dinosaurs might have produced. Computer simulations play a crucial role in this field of study. Scientists create detailed digital models of dinosaur vocal tracts based on fossil evidence. These models can then be used to simulate the passage of air through the reconstructed vocal organs, generating potential dinosaur sounds. This technique has led to some fascinating insights, suggesting that some dinosaurs may have produced low-frequency rumbles similar to those of modern crocodiles. Comparisons with living relatives of dinosaurs, such as birds and crocodiles, also provide valuable clues. By studying the vocalizations and vocal organs of these modern animals, scientists can draw parallels and make inferences about their ancient relatives. For instance, the discovery that some dinosaurs possessed a syrinx, the vocal organ found in modern birds, has led to speculation that these dinosaurs might have been capable of more complex vocalizations than previously thought. Paleontologists also examine other anatomical features that might have influenced dinosaur vocalizations. The size and shape of the skull, the structure of the inner ear, and even the presence of certain facial features can all provide hints about how dinosaurs might have communicated vocally. While these methods cannot provide definitive answers, they allow scientists to piece together a compelling picture of dinosaur vocalizations, bringing us closer to understanding how these fascinating creatures might have sounded in their ancient world. While we can't be certain if dinosaurs sang exactly like modern birds, recent research suggests that some dinosaurs may have had similar vocal abilities. Paleontologists have discovered fossilized voice boxes, called syrinxes, in ancient bird relatives that lived alongside dinosaurs. These findings indicate that the capacity for bird-like vocalizations existed during the age of dinosaurs. The closest living relatives of dinosaurs are birds, which evolved from a group of dinosaurs called theropods. Many of these theropod dinosaurs, particularly those in the Maniraptoran group, shared numerous features with modern birds, including feathers and hollow bones. It's plausible that some of these dinosaurs also possessed vocal organs capable of producing complex sounds. Some scientists speculate that certain dinosaurs, especially smaller feathered species, might have used vocalizations for communication, territorial displays, or mating calls. These sounds could have ranged from chirps and whistles to more elaborate melodies. However, larger dinosaurs likely produced deeper, louder sounds, more akin to the low-frequency calls of modern crocodiles or the resonant sounds of large birds like cassowaries. While we may never know the exact sounds dinosaurs made, ongoing research in paleontology and evolutionary biology continues to shed light on the vocal capabilities of these ancient creatures. The possibility of singing dinosaurs adds another fascinating dimension to our understanding of prehistoric life and the evolutionary link between dinosaurs and modern birds. The structure of dinosaur throats provides fascinating insights into the sounds these ancient creatures might have made. Paleontologists have carefully examined fossilized remains of dinosaur vocal organs, particularly the syrinx, which is the sound-producing organ in birds, the living descendants of dinosaurs. By studying these structures, scientists can make educated guesses about the vocalizations of different dinosaur species. For instance, some dinosaurs like hadrosaurs, also known as duck-billed dinosaurs, had elaborate nasal passages and hollow crests. These structures likely acted as resonating chambers, allowing them to produce loud, low-frequency sounds similar to a foghorn or tuba. This suggests that these dinosaurs could communicate over long distances, possibly for mating calls or to warn of approaching predators. In contrast, the throat structure of some predatory dinosaurs like Tyrannosaurus rex indicates they might have produced deeper, more guttural sounds. Their large size and powerful chest muscles could have supported the production of low-frequency vocalizations that carried far and possibly intimidated prey or rivals. However, it is important to note that soft tissues rarely fossilize, making it challenging to draw definitive conclusions about dinosaur vocalizations. Scientists continue to study modern birds and crocodilians, the closest living relatives of dinosaurs, to better understand how dinosaur throat structures might have functioned and the range of sounds they could have produced. Dinosaur hearing and vocalizations were diverse and complex, reflecting the wide variety of species that existed over their long reign. Many dinosaurs likely had acute hearing abilities, particularly adapted to detect sounds within their specific environments and social groups. The structure of dinosaur ear bones and cochlea suggests that different species were attuned to various frequency ranges. Some, like the large sauropods, might have been sensitive to low-frequency sounds, potentially allowing them to communicate over long distances. Others, such as smaller predators, may have had hearing more suited to higher frequencies, useful for detecting prey or alerting them to danger. Regarding vocalizations, evidence from fossilized voice boxes and comparisons with modern relatives like birds and crocodiles indicate that dinosaurs were likely capable of producing a range of sounds. These could have included low rumbles, hisses, roars, and even bird-like calls in some species. The hollowed crests of certain dinosaurs, such as Parasaurolophus, might have functioned as resonating chambers, amplifying their calls. The relationship between dinosaur hearing and vocalizations was likely a crucial aspect of their behavior and ecology. It would have played a role in everything from territorial disputes and mating rituals to coordinating herds and parent-offspring communication. This intricate interplay between sound production and reception continues to fascinate paleontologists as they uncover more about the sensory world of these ancient creatures. Dinosaurs, like many modern animals, likely had distinctive vocalizations that varied between species and potentially even within species across different regions. While we cannot directly observe or record dinosaur sounds, paleontologists have made educated inferences based on fossil evidence and comparisons with living relatives. The structure of dinosaur vocal organs, particularly in some species, suggests they were capable of producing a range of sounds. For instance, the hollow crests of hadrosaurs or duck-billed dinosaurs might have functioned as resonance chambers, allowing them to create unique calls. These calls could have differed between hadrosaur species and possibly even between populations in different areas. Evidence from modern birds, which are direct descendants of certain dinosaur lineages, supports the idea of regional variations in dinosaur vocalizations. Many bird species exhibit distinct regional dialects, with individuals from different areas producing slightly different versions of their species' typical calls. This phenomenon could have existed in their dinosaur ancestors as well. It is important to note that not all dinosaurs would have been equally vocal. Some may have relied more on visual displays or other forms of communication. However, for those that did vocalize, it is plausible that regional differences emerged over time as populations adapted to local environments and developed unique social structures. The evolution of dinosaur sounds is a fascinating area of study, though much of our understanding comes from inference and educated guesses based on fossil evidence and comparisons with modern animals. As dinosaurs evolved over millions of years, their vocalizations likely changed to suit their environments and social needs. Early dinosaurs, such as the small, agile theropods of the Triassic period, probably made simple chirps or clicks, similar to those of modern lizards. These sounds would have been useful for basic communication within small groups or between mates. As dinosaurs diversified and grew larger during the Jurassic period, their vocal abilities likely expanded. The development of air sacs in sauropods and some theropods would have allowed for more resonant calls. These long-necked giants might have produced low-frequency rumbles that could travel great distances, useful for communicating across the vast plains they inhabited. Meanwhile, ceratopsians like Triceratops likely developed more complex vocalizations for herd communication and territorial displays. By the late Cretaceous period, some dinosaurs had evolved highly sophisticated vocal abilities. Hadrosaurs, often called duck-billed dinosaurs, possessed elaborate hollow crests that likely functioned as resonating chambers. These structures could have produced a range of trumpeting calls, perhaps allowing for complex social interactions within their herds. The evolution of dinosaur sounds reflects the increasing complexity of their social structures and ecological roles over time. Sound likely played a crucial role in dinosaur communication, much as it does for many modern animals. While we cannot directly observe or record dinosaur vocalizations, scientific evidence suggests that these ancient creatures used a variety of sounds to interact with one another. Large dinosaurs, such as the long-necked sauropods, may have produced low-frequency rumbles that could travel over long distances. These infrasonic sounds, similar to those used by modern elephants, would have been ideal for communication across the vast prehistoric landscapes. Such low-frequency calls could have served multiple purposes, including attracting mates, warning of predators, or coordinating group movements. Smaller dinosaurs, particularly those related to modern birds, likely had a more diverse vocal repertoire. Fossil evidence of specialized throat structures in some species suggests they were capable of producing complex sounds. These vocalizations might have ranged from chirps and whistles to more elaborate songs, used for territorial displays or courtship rituals. Paleontologists have also found evidence of resonating chambers in the crests of some dinosaurs, such as the hadrosaurs or duck-billed dinosaurs. These structures could have amplified sounds, allowing these dinosaurs to produce loud, distinctive calls. These vocalizations might have helped members of the same species recognize each other or signal across herds. The diversity of potential dinosaur sounds reminds us that the prehistoric world was likely filled with a cacophony of animal voices, each playing a vital role in the complex social lives of these fascinating creatures. Some scientists believe that certain dinosaur species may have been capable of producing infrasound similar to modern animals like elephants and whales. This theory is based on the physical characteristics of some dinosaurs, particularly the long-necked sauropods. Sauropods, such as Brachiosaurus and Diplodocus, had enormous body sizes and long necks that could have acted as resonating chambers. These features might have allowed them to generate low-frequency sounds below the range of human hearing, known as infrasound. These sounds can travel long distances and could have been used for communication between members of the same species. The ability to produce infrasound could have served several purposes for dinosaurs. It might have been used to signal danger, coordinate group movements, or even as a form of long-distance mating call. In modern animals, infrasound is known to carry for miles, allowing communication over vast areas. While this idea remains speculative, ongoing research in paleoacoustics continues to explore the possible sound-producing capabilities of extinct animals. By studying the anatomical structures of dinosaur fossils and comparing them to modern animals known to produce infrasound, scientists hope to gain a better understanding of dinosaur communication and behavior. Dinosaur sounds in popular media are largely speculative and often inaccurate. Despite what we hear in movies and television shows, scientists have very limited evidence of what dinosaurs actually sounded like. The roars and screeches commonly associated with these ancient creatures are more a product of creative imagination than scientific fact. Paleontologists have made some educated guesses about dinosaur vocalizations based on the creature's anatomy and their closest living relatives. For instance, some dinosaurs had hollow crests that might have been used to produce resonant calls, similar to how some modern birds use air sacs to amplify their songs. However, the exact nature of these sounds remains unknown. Recent research suggests that many dinosaurs, particularly the larger ones, might have produced low-frequency sounds that humans would barely hear. These infrasonic rumbles, similar to those made by elephants and alligators today, could have traveled long distances for communication. Other dinosaurs might have hissed, clapped their jaws, or created sounds by rubbing scales together, much like some modern reptiles do. It is important to note that the iconic Tyrannosaurus Rex roar from popular culture is particularly unlikely. Being more closely related to birds than to lions or bears, T-Rex might have made sounds more akin to the low booms of large birds like cassowaries or emus, rather than the terrifying roar we have come to expect. As research continues, our understanding of dinosaur sounds may change, but for now, much of what we hear in media remains more fiction than fact. Dinosaurs exhibited a wide range of social behaviors, from solitary lifestyles to complex group dynamics. Evidence from fossil records and trackways has provided paleontologists with valuable insights into dinosaur sociality. Many large herbivorous dinosaurs, such as Brachiosaurus and Diplodocus, likely lived in herds. These massive creatures would have benefited from the protection and collective awareness that group living provides. Fossil beds containing multiple individuals of the same species support this theory. Smaller herbivores like Psittacosaurus also show evidence of group living, with fossils of adults found alongside juveniles suggesting parental care. Carnivorous dinosaurs displayed varied social structures. Some, like Tyrannosaurus rex, were long thought to be solitary hunters. However, recent evidence suggests they might have hunted in family groups. Smaller carnivores such as Deinonychus and Velociraptor likely hunted in packs, using coordinated attacks to bring down larger prey. This cooperative behavior would have required sophisticated communication and social bonds. Perhaps the most compelling evidence of dinosaur sociality comes from track sites. Parallel trackways of multiple individuals moving in the same direction indicate group travel. These fossilized footprints provide a snapshot of dinosaur behavior frozen in time, offering direct evidence of their social nature. As research continues, our understanding of dinosaur social structures continues to evolve, revealing a complex and diverse range of behaviors among these ancient creatures. Fossil evidence provides compelling support for the existence of dinosaur herds. Paleontologists have discovered numerous bone beds containing the remains of multiple individuals from the same species, often spanning different age groups. These mass assemblages suggest that many dinosaurs lived and died together in social groups. Trackways, or fossilized footprints, offer another line of evidence. Scientists have found extensive sets of parallel tracks made by the same species, indicating groups of dinosaurs moving in the same direction at the same time. Some of these trackways even show evidence of adults and juveniles traveling together, hinting at family structures within herds. Comparative studies with modern animals also support the herd hypothesis. Many living dinosaur relatives, such as birds and crocodiles, exhibit social behaviors. This suggests that their ancient ancestors may have possessed similar tendencies. Additionally, herd behavior offers numerous evolutionary advantages, including protection from predators and more efficient foraging, which would have benefited dinosaurs as well. The discovery of nesting sites with multiple nests in close proximity further reinforces the idea of dinosaur sociality. These sites imply that some species gathered in large numbers during breeding seasons, much like many modern birds and reptiles do today. Taken together, these various lines of evidence paint a picture of dinosaurs as social creatures, with many species likely forming herds as a crucial survival strategy. Many dinosaur species exhibited complex social behaviors, suggesting the presence of intricate social structures. Paleontologists have uncovered evidence of herd behavior in various dinosaur groups, particularly among herbivorous species. Fossil discoveries of large groups of dinosaurs preserved together indicate that some species lived and traveled in herds, potentially for protection, foraging, or migration purposes. One notable example is the hadrosaurs, also known as duck-billed dinosaurs. These herbivores left behind extensive fossil beds containing thousands of individuals, suggesting they lived in massive herds. Scientists believe these groups may have had age-based hierarchies and communal nesting sites, demonstrating a level of social organization. Ceratopsians, such as Triceratops, also show evidence of social behavior. Bone beds containing multiple individuals of varying ages suggest they may have lived in family groups or larger herds. Some researchers propose that the elaborate frills and horns of these dinosaurs may have played a role in social displays and communication within their groups. Theropod dinosaurs, including some species related to Tyrannosaurus rex, have been found in small groups, hinting at possible pack hunting behaviors. While the extent of their social structures remains debated, these findings suggest that even predatory dinosaurs may have engaged in cooperative behaviors. As research continues, our understanding of dinosaur social structures continues to evolve, revealing a more complex picture of prehistoric life. Sociability played a crucial role in shaping dinosaur survival strategies, influencing their behavior, reproduction, and overall success as a group. Many dinosaur species evolved complex social structures that enhanced their ability to thrive in diverse environments. For herbivorous dinosaurs, living in herds provided numerous advantages. Large groups offered better protection against predators, with more eyes and ears to detect danger. This collective vigilance allowed individuals to spend more time feeding and less time on high alert. Herding behavior also benefited young dinosaurs who could learn from older, more experienced members of the group. Carnivorous dinosaurs also developed social behaviors, though often in smaller groups. Pack hunting allowed these predators to take down larger prey, increasing their food supply and chances of survival. Some evidence suggests that certain carnivorous species may have engaged in cooperative breeding, with multiple adults caring for young in a shared nest. Sociability also influenced dinosaur communication and mating strategies. Many species developed elaborate visual displays, such as colorful feathers or distinctive head crests, which likely played a role in attracting mates and establishing dominance within social groups. These adaptations highlight the complex interplay between social behavior and evolutionary success in the dinosaur world. Dinosaurs exhibited a wide range of hunting behaviors, including solitary predation. While many dinosaur species were social hunters operating in packs or family groups, there were indeed solitary predators among them. One of the most famous solitary hunters was Tyrannosaurus rex, the iconic apex predator of the late Cretaceous period. This massive theropod, standing up to 12 meters long, likely hunted alone, using its powerful jaws and keen senses to track and ambush prey. Its size and strength allowed it to take down large herbivores without assistance from others of its kind. Another example of a solitary predator was Allosaurus, a large carnivorous dinosaur from the late Jurassic period. Fossil evidence suggests that Allosaurus hunted independently, relying on its agility and sharp teeth to bring down prey. Similarly, smaller theropods like Velociraptor, contrary to their portrayal in popular media, may have hunted alone or in small groups, using their intelligence and speed to their advantage. The presence of solitary predators among dinosaurs highlights the diversity of hunting strategies that evolved over millions of years. These lone hunters played crucial roles in their ecosystems, helping to maintain balance and drive the evolution of their prey species. Dinosaur social behavior underwent significant changes throughout their long reign on Earth. Early dinosaurs, which first appeared around 230 million years ago, likely exhibited simpler social structures. These early species, such as the small carnivorous Coelophysis, probably lived and hunted in loose groups, but evidence for complex social interactions is limited. As dinosaurs diversified and grew larger during the Jurassic period, about 200 to 145 million years ago, more sophisticated social behaviors began to emerge. Sauropods, the long-necked plant eaters, started to form herds for protection and more efficient foraging. This behavior is supported by fossil evidence of multiple individuals found together and the presence of trackways showing groups moving in the same direction. The evolution of social behavior reached its peak in the Cretaceous period from 145 to 66 million years ago. Many dinosaur species developed intricate social structures during this time. Ceratopsians, like Triceratops, likely lived in large herds, as suggested by bone beds containing numerous individuals. These herds may have provided protection from predators and facilitated mating rituals. Perhaps the most complex social behaviors evolved among the theropods, particularly in dromaeosaurids and other bird-like dinosaurs. Fossil evidence indicates that some species, such as Deinonychus, hunted in packs, coordinating their attacks on larger prey. This cooperative hunting strategy represents a significant leap in social complexity, requiring communication and coordination among individuals. The evolution of dinosaur social behavior ultimately culminated in the highly social behaviors seen in modern birds, the living descendants of certain theropod dinosaurs. Fossil trackways offer invaluable insights into dinosaur social behavior, providing a window into the prehistoric past that bones alone cannot reveal. These preserved footprints allow paleontologists to study how dinosaurs moved and interacted with one another, offering clues about their daily lives and social structures. One of the most significant revelations from trackways is evidence of herding behavior in many dinosaur species. Multiple sets of footprints moving in the same direction and at the same pace suggest that some dinosaurs traveled in groups, possibly for protection or during migrations. This behavior has been observed in tracks left by both herbivores and carnivores, indicating that social cooperation was widespread among different dinosaur types. Trackways have also shed light on potential parenting behaviors. Some sites show large footprints accompanied by smaller ones, suggesting adults walking alongside juveniles. This could indicate that certain dinosaur species cared for their young for extended periods, much like modern birds and some reptiles do today. Furthermore, fossil trackways can reveal information about dinosaur courtship and mating rituals. Unusual patterns in some tracks suggest display behaviors, where dinosaurs may have engaged in elaborate dances or movements to attract mates. These fossilized snapshots of behavior provide fascinating glimpses into the complex social lives of creatures that roamed the Earth millions of years ago, helping scientists piece together a more complete picture of dinosaur ecology and social structures. The size of dinosaurs played a crucial role in shaping their social behaviors and interactions. Larger dinosaur species often exhibited more complex social structures compared to their smaller counterparts. This relationship between size and sociability was influenced by several factors, including resource requirements, predator defense, and reproductive strategies. For massive herbivores like sauropods, which could reach lengths of over 100 feet, living in herds provided significant advantages. These gentle giants likely traveled in family groups or larger aggregations, offering protection against predators and allowing for more efficient foraging. Their sheer size made them less vulnerable to attacks, but moving in groups further enhanced their safety. In contrast, many smaller dinosaurs, particularly carnivorous species, tended to be more solitary or form smaller family units. However, some exceptions existed, such as the pack-hunting behavior observed in certain medium-sized theropods, like Deinonychus. These social hunters used their collective strength to take down prey much larger than themselves, demonstrating that size was not the sole determinant of sociability. Interestingly, the largest carnivorous dinosaurs, such as Tyrannosaurus rex, were likely less social than their smaller relatives. Their immense size and high energy requirements made it challenging to sustain large groups, leading to more solitary lifestyles. This showcases how extreme size could sometimes limit social interactions among dinosaurs, creating a complex relationship between physical dimensions and social behaviors in these ancient creatures. Paleontologists have long debated whether dinosaurs engaged in cooperative hunting behaviors. While direct evidence is limited due to the challenges of fossilization, some findings suggest that certain dinosaur species might have hunted in groups. One of the most compelling cases for cooperative hunting comes from the study of dromaeosaurids, a family of swift, agile predators that includes Velociraptor and Deinonychus. Fossil evidence indicates that these dinosaurs had relatively weak jaws and small teeth compared to their body size, which has led some researchers to propose that they might have hunted in packs to take down larger prey. Further support for this theory comes from fossilized trackways discovered in various locations around the world. These preserved footprints sometimes show multiple individuals of the same species moving in the same direction, potentially indicating group behavior. However, it is important to note that such evidence does not definitively prove cooperative hunting, as the animals could have been migrating or moving together for other reasons. Some scientists also point to modern-day relatives of dinosaurs, such as birds and crocodiles, which sometimes exhibit cooperative hunting behaviors. This connection suggests that their ancient ancestors might have possessed similar capabilities. However, without direct observation, the extent and nature of dinosaur cooperative hunting remain a subject of ongoing research and speculation in the field of paleontology. Recent paleontological discoveries have revolutionized our understanding of dinosaur social behavior, transforming our perception of these ancient creatures from solitary, cold-blooded reptiles to complex social animals. Evidence from fossil beds and trackways suggests that many dinosaur species lived in herds, packs, or family groups, much like modern animals. For instance, studies of hadrosaur nesting sites reveal that these duck-billed dinosaurs cared for their young in large nesting colonies, similar to today's seabirds. This nurturing behavior indicates a level of parental care previously unexpected in reptiles. Likewise, fossil evidence of theropods like Deinonychus suggests they hunted in coordinated packs, challenging the notion of dinosaurs as purely instinct-driven predators. Furthermore, the discovery of vast bone beds containing multiple individuals of the same species, such as the horned dinosaur Centrosaurus, implies that some dinosaurs gathered in large herds for protection or migration. This social organization hints at complex intraspecies communication and hierarchical structures within dinosaur groups. These insights into dinosaur sociability paint a picture of dynamic, interactive creatures rather than the lumbering, solitary beasts often portrayed in popular culture. By recognizing the social complexity of dinosaurs, we gain a deeper appreciation for their ecological roles and evolutionary success, bridging the gap between these ancient animals and the diverse social behaviors observed in modern species. Dinosaurs roamed the Earth for over 160 million years, evolving into a diverse array of species with varying levels of intelligence. While it's challenging to determine exact cognitive abilities of extinct animals, paleontologists have made significant discoveries about dinosaur brains and behavior that offer insights into their intelligence. Some dinosaurs, particularly those in the theropod group, which includes species like Tyrannosaurus rex and Velociraptor, showed signs of relatively advanced cognitive abilities. These predators had larger brain-to-body size ratios, suggesting they possessed sharper senses, better coordination, and potentially higher problem-solving skills. Fossil evidence indicates that some of these dinosaurs hunted in packs, implying a level of social intelligence and cooperation. Certain herbivorous dinosaurs, such as Stegosaurus, had comparatively smaller brains relative to their body size. However, this doesn't necessarily mean they were unintelligent. These dinosaurs likely had the mental capacity required for their survival, including recognizing food sources, avoiding predators, and engaging in social behaviors within their herds. Recent studies of dinosaur endocasts, which are molds of the brain cavity, have revealed that some species had well-developed areas associated with sight, smell, and balance. This suggests that dinosaurs were well adapted to their environments and possessed the necessary cognitive tools to thrive in their respective ecological niches for millions of years. Paleontologists employ several ingenious techniques to estimate dinosaur intelligence, despite the immense time gap separating us from these ancient creatures. One key method involves examining the size and shape of fossilized brain cases. By creating detailed casts of the brain cavity, scientists can make educated guesses about brain size relative to body mass, a metric known as the encephalization quotient. This ratio provides clues about potential cognitive abilities, as larger brain-to-body ratios often correlate with higher intelligence in modern animals. Another approach focuses on analyzing the sensory capabilities of dinosaurs. By studying the size and structure of eye sockets, olfactory bulbs, and inner ear canals, researchers can infer how well these animals could see, smell, and maintain balance. More developed senses might indicate a greater need for processing complex environmental information, suggesting higher intelligence. Paleontologists also examine dinosaur behavior through trace fossils like footprints and nesting sites. Evidence of complex social behaviors, such as herding or coordinated hunting, can imply higher cognitive functions. Additionally, comparisons with modern relatives like birds and crocodiles provide valuable insights, as these animals share common ancestors with dinosaurs and may exhibit similar cognitive traits. Lastly, studying the evolutionary arms race between predators and prey can offer clues about dinosaur intelligence. More sophisticated hunting or defense strategies might indicate higher levels of problem-solving abilities and adaptability, key components of intelligence. While these methods cannot provide definitive answers, They allow scientists to piece together a fascinating picture of dinosaur cognition. Determining dinosaur intelligence is a challenging task for paleontologists, as brain tissue does not fossilize. However, scientists have developed methods to estimate cognitive abilities based on brain case size and structure. Among the most intelligent dinosaurs were likely the small, agile theropods, particularly those belonging to the dromaeosaurid family. Troodon stands out as a prime candidate for high intelligence among dinosaurs. This small carnivore had a large brain relative to its body size, stereoscopic vision, and grasping hands, all indicators of advanced problem-solving abilities. Deinonychus, a close relative of Velociraptor, also exhibited signs of higher intelligence, with a brain-to-body ratio comparable to that of modern birds. Interestingly, some herbivorous dinosaurs also showed signs of advanced cognition. Stegosaurus, despite its reputation for having a walnut-sized brain, actually had a complex neural structure in its hip region, which might have acted as a secondary brain for coordinating movement and processing sensory information. It is worth noting that dinosaur intelligence should not be compared directly to mammalian intelligence. The brain structures and cognitive processes of dinosaurs were likely quite different from those of mammals, making direct comparisons problematic. Nonetheless, these ancient creatures clearly possessed varying degrees of problem-solving abilities and adaptability, allowing them to thrive in diverse environments for millions of years. Dinosaur brain size varied greatly across different species, but generally, their brains were small compared to their massive bodies. This relationship between brain and body size is called the encephalization quotient. For most dinosaurs, this ratio was lower than what we see in modern mammals and birds. Take the Stegosaurus, for instance. This herbivorous dinosaur from the late Jurassic period had a body that could weigh up to 6,000 kilograms, yet its brain was only about the size of a walnut. Similarly, the long-necked sauropods, some of the largest animals to ever walk the earth, had brains that were tiny in proportion to their enormous bodies. However, not all dinosaurs had such small brains relative to their size. Some theropod dinosaurs, particularly those in the line that led to birds, had larger brain-to-body ratios. The Tyrannosaurus rex, for example, had a brain size comparable to that of modern reptiles relative to its body. Velociraptors and their relatives had even larger brains for their body size, suggesting they may have been capable of more complex behaviors. This variation in brain-to-body ratios among dinosaurs provides fascinating insights into their potential cognitive abilities and behaviors. It also highlights the evolutionary path that eventually led to the highly encephalized birds we see today, which are the living descendants of certain dinosaur lineages. As far as we currently know, there were no tool-using dinosaurs. The concept of dinosaurs using tools is more science fiction than scientific fact. Dinosaurs ruled the Earth for over 160 million years, but they never developed the cognitive abilities or physical adaptations necessary for tool use. The ability to use tools requires a combination of intelligence, problem-solving skills, and physical dexterity that we have not found evidence for in dinosaur species. While some dinosaurs, like the Velociraptor, had relatively large brain-to-body size ratios, their brains were still primarily devoted to basic survival functions rather than complex cognition. It is worth noting that tool use is not exclusive to humans. Some modern animals, such as chimpanzees and crows, have been observed using simple tools. However, this behavior emerged long after the extinction of dinosaurs. The earliest evidence of tool use by our hominid ancestors dates back to about 3.3 million years ago, which is over 60 million years after the dinosaurs disappeared. The absence of tool-using dinosaurs does not diminish their fascinating nature. These creatures evolved a wide array of impressive adaptations, from the massive size of sauropods to the deadly claws of theropods, allowing them to thrive in various environments without the need for tools. Dinosaur intelligence remains a fascinating area of study, with new discoveries constantly reshaping our understanding. Comparing dinosaur cognition to that of modern birds and reptiles offers intriguing insights into the evolutionary development of intelligence. Recent research suggests that some dinosaurs, particularly theropods like Tyrannosaurus rex and Velociraptor, possessed cognitive abilities that may have rivaled or even surpassed those of modern reptiles. These dinosaurs had relatively large brain-to-body size ratios, indicating the potential for more advanced problem-solving and social behaviors. Interestingly, modern birds, which are direct descendants of certain dinosaur lineages, often demonstrate higher levels of intelligence than most reptiles. This suggests that the cognitive capabilities of some dinosaurs might have been closer to those of birds than to modern reptiles. For instance, evidence of complex social behaviors and potential tool use in certain dinosaur species aligns more closely with observed behaviors in birds than in most reptiles. However, it's crucial to note that intelligence varies widely among both modern birds and reptiles. Some birds, like corvids and parrots, show remarkable problem-solving skills and even self-awareness, while certain reptiles, such as monitor lizards, display unexpected cognitive abilities. This diversity reminds us that dinosaur intelligence likely spanned a broad spectrum, with some species potentially possessing sophisticated cognitive skills, while others may have had more limited capabilities. Dinosaurs roamed the Earth for over 160 million years, evolving into a diverse array of species with varying levels of intelligence. While we cannot directly observe their behavior, paleontologists have uncovered evidence suggesting that some dinosaur species possessed problem-solving abilities. The most compelling evidence comes from the family of dinosaurs known as theropods, which includes species like Tyrannosaurus rex and Velociraptor. These carnivorous dinosaurs had relatively large brain sizes compared to their body mass, a trait often associated with higher cognitive functions. Fossil evidence indicates that some theropods, particularly the dromaeosaurids, had binocular vision and enlarged areas of the brain responsible for processing visual information, suggesting they were capable of complex hunting strategies. Troodontids, another group of small, bird-like theropods, had even larger brain-to-body size ratios, comparable to those of modern birds. This suggests they may have had the capacity for more advanced problem-solving and learning. Some scientists speculate that these dinosaurs might have been able to use simple tools or solve basic puzzles to access food, similar to how some modern birds do. Recent studies of dinosaur nesting sites have also revealed intriguing insights. Some species, such as the duck-billed hadrosaurs, created complex nesting colonies that required social cooperation and possibly problem-solving skills to maintain. The ability to work together and adapt to changing environmental conditions suggests a level of cognitive flexibility that goes beyond simple instinctual behavior. Intelligence among dinosaur species varied widely, reflecting the diverse ecological niches they occupied over their long reign on Earth. The most advanced cognitive abilities were found in theropods, particularly among the dromaeosaurids and troodontids. These swift, predatory dinosaurs possessed relatively large brains for their body size, suggesting enhanced problem-solving skills and potentially complex social behaviors. Troodon, often considered one of the most intelligent dinosaurs, had a brain size comparable to that of modern birds. Its large eyes and binocular vision hint at keen hunting abilities and possibly nocturnal habits, requiring advanced spatial awareness and memory. Similarly, Velociraptor and its relatives likely exhibited pack-hunting behaviors, necessitating a degree of social intelligence and cooperation. In contrast, large herbivorous dinosaurs such as sauropods had much smaller brains relative to their body size. However, this does not necessarily indicate low intelligence, as they successfully navigated complex environments and maintained social structures. Stegosaurs and other armored dinosaurs had notably small brain-to-body ratios, suggesting their survival relied more on physical defenses than cognitive abilities. Ceratopsians and hadrosaurs, with their complex social behaviors and potential migratory patterns, likely possessed moderate intelligence. Their ability to live in herds and care for young implies a level of social cognition. Overall, dinosaur intelligence was as varied as the creatures themselves, each adapted to its specific lifestyle and environmental challenges. Intelligence played a significant role in dinosaur evolution, shaping their behavior, survival strategies, and ultimately their success as a dominant group of animals for over 160 million years. Contrary to popular misconceptions, many dinosaur species exhibited remarkable cognitive abilities that contributed to their adaptability and longevity. Fossil evidence and comparative studies with modern relatives suggest that some dinosaurs possessed problem-solving skills and social intelligence. Theropods, the group that includes Velociraptor and Tyrannosaurus rex, showed signs of enhanced brain development, particularly in areas associated with sensory processing and motor control. This cognitive advancement likely improved their hunting strategies and ability to navigate complex environments. Herbivorous dinosaurs also benefited from increased intelligence. Species like Triceratops and Stegosaurus evolved sophisticated social behaviors, possibly including herding and cooperative defense against predators. Their ability to communicate and work together enhanced their chances of survival in a world filled with formidable carnivores. Perhaps most intriguingly, the evolution of intelligence in dinosaurs laid the groundwork for the remarkable cognitive abilities seen in their descendants, birds. The progressive development of dinosaur brains over millions of years set the stage for the emergence of avian intelligence, which continues to astonish scientists today. This evolutionary journey highlights the critical role of intelligence in shaping the diverse and fascinating world of dinosaurs and their lasting impact on Earth's ecosystems. Our perception of dinosaur intelligence has undergone a remarkable transformation since their fossils were first discovered. Initially, dinosaurs were viewed as slow, dim-witted creatures, little more than lumbering lizards. This misconception persisted for decades, reinforced by early paleontological studies that focused primarily on their physical characteristics rather than their cognitive abilities. However, as research techniques advanced and new fossil discoveries came to light, scientists began to paint a very different picture of dinosaur intelligence. The discovery of complex social behaviors, particularly among theropods like velociraptors, suggested levels of coordination and problem-solving far beyond what was previously imagined. Evidence of pack hunting, elaborate mating rituals, and even potential parental care hinted at sophisticated social structures and communication. Brain-to-body size ratios, a rough indicator of intelligence, have been reassessed for many dinosaur species. Some, like the small bird-like Troodon, have been found to possess ratios comparable to modern birds, which are known for their cognitive abilities. This has led to a re-evaluation of dinosaur learning capabilities and adaptability. Recent studies have also revealed that some dinosaurs possessed keen senses, particularly vision and smell, which would have required significant neural processing power. The realization that many dinosaurs were warm-blooded has further supported the idea of more active, intelligent creatures than once believed. Today, while we still have much to learn, dinosaurs are increasingly viewed as complex, adaptable animals with levels of intelligence that would have rivaled many modern-day creatures. Many dinosaur species did indeed migrate, similar to how modern animals undertake seasonal journeys today. Evidence from fossil records and geological studies suggests that various dinosaur groups embarked on long-distance travels, often in response to changing environmental conditions or in search of food and water. One notable example is the hadrosaurs, also known as duck-billed dinosaurs. Paleontologists have found evidence that these herbivores migrated across vast distances in what is now Alaska. They likely moved between coastal lowlands and inland areas, following the growth of vegetation as seasons changed. Sauropods, the long-necked giants of the dinosaur world, also showed migratory behaviors. Fossil trackways discovered in various parts of the world indicate that these massive creatures traveled in herds, possibly to find new feeding grounds or to reach nesting sites. Climate played a crucial role in dinosaur migrations. As temperatures fluctuated and rainfall patterns shifted, dinosaurs would have needed to adapt by moving to more favorable areas. This behavior helped them survive in a constantly changing world, much like how modern animals migrate to cope with seasonal variations. Paleontologists have uncovered compelling evidence suggesting that dinosaurs engaged in seasonal migrations, much like many modern animals do today. Fossil trackways discovered in various locations around the world provide some of the most direct evidence for dinosaur movement patterns. These preserved footprints, sometimes stretching for miles, indicate that large groups of dinosaurs traveled together in specific directions. Bone histology studies offer another line of evidence. By examining the microscopic structure of fossilized bones, scientists can determine growth patterns and detect signs of seasonal stress. These stress markers often coincide with periods when food might have been scarce, suggesting that some dinosaurs may have migrated to find better feeding grounds. Isotope analysis of fossilized teeth and bones has also yielded valuable insights. Different geographical areas have distinct isotopic signatures based on local water and plant life. When dinosaur remains show isotope patterns that change over time, it indicates the animal moved between different regions during its lifetime. Furthermore, the discovery of dinosaur fossils in extreme environments, such as prehistoric polar regions, suggests that some species undertook long-distance migrations to take advantage of seasonal resources. This behavior would have allowed them to exploit abundant food sources during polar summers while avoiding harsh winter conditions. Collectively, these lines of evidence paint a picture of dinosaurs as dynamic creatures capable of undertaking impressive journeys across ancient landscapes. Dinosaurs were remarkable creatures that roamed the earth for millions of years, and their migratory patterns varied greatly depending on the species and environmental conditions. Some dinosaurs likely undertook impressive journeys across vast distances, while others may have stayed within more localized areas. Large herbivorous dinosaurs, such as the long-necked sauropods, are believed to have been capable of traveling hundreds of miles during their seasonal migrations. These massive creatures, weighing up to 70 tons, would have needed to cover extensive ground to find sufficient food and water sources. Fossil evidence suggests that some sauropod herds might have traversed distances of up to 300 miles in search of more favorable conditions. Smaller dinosaurs, like the duck-billed hadrosaurs, also engaged in seasonal migrations, though perhaps not as extensive as their larger counterparts. Studies of fossilized teeth and bone samples indicate that some hadrosaur species might have traveled between 50 and 100 miles between their summer and winter ranges. These migrations would have been crucial for finding food and avoiding harsh weather conditions. Interestingly, not all dinosaurs were migratory. Some species, particularly those adapted to specific environments or with more limited mobility, likely remained in relatively small territories throughout their lives. The key factors influencing dinosaur migration patterns would have included climate changes, food availability, and breeding cycles, much like the migratory behaviors we observe in modern animals today. Dinosaur migration patterns were shaped by a complex interplay of environmental and biological factors. Climate change played a crucial role, as shifting temperatures and rainfall patterns forced dinosaurs to move in search of more favorable conditions. Seasonal variations prompted many species to undertake regular journeys, following food sources as they became available in different regions throughout the year. Food availability was a primary driver of dinosaur movement. Herbivorous dinosaurs would travel to find fresh vegetation, while carnivores followed their prey. This created a domino effect, with entire ecosystems shifting across landscapes. Geological events, such as volcanic eruptions or the formation of new land bridges, also influence migration routes by altering the physical landscape and opening up new territories for exploration. Competition for resources among different dinosaur species likely contributed to migration patterns as well. As populations grew, some groups may have been forced to seek out new habitats to avoid overcrowding and resource depletion. Additionally, breeding behaviors could have prompted seasonal movements, with dinosaurs traveling to specific nesting grounds or mating areas. Recent fossil evidence suggests that some dinosaur species undertook long-distance migrations crossing thousands of kilometers. These epic journeys were likely driven by a combination of factors, including changes in daylight hours, temperature fluctuations, and the need to find suitable breeding grounds. Understanding these ancient migration patterns provides valuable insights into dinosaur behavior and the dynamic nature of prehistoric ecosystems. Migration played a crucial role in shaping dinosaur evolution and speciation over millions of years. As dinosaurs moved across continents and adapted to new environments, they developed unique traits and behaviors that led to the emergence of diverse species. During the Mesozoic era, when dinosaurs roamed the Earth, the continents were arranged differently than they are today. Land masses were connected, allowing dinosaurs to travel vast distances and colonize new territories. This movement exposed them to varied climates, food sources, and predators, driving adaptations that resulted in new species. One notable example is the hadrosaurs, or duck-billed dinosaurs. These herbivores likely originated in Asia but spread to North America via land bridges. As they encountered new plant species and environmental pressures, they evolved specialized teeth and jaw structures to process different types of vegetation. This led to the development of numerous hadrosaur species across both continents. Migration also influenced the evolution of predatory dinosaurs. As prey species moved and adapted, carnivores had to evolve new hunting strategies and physical characteristics to keep pace. This ongoing evolutionary arms race between predator and prey, driven in part by migration, contributed to the incredible diversity of dinosaur species that existed throughout the Mesozoic era. Evidence suggests that some dinosaur species did engage in seasonal migrations, similar to many modern animals. Paleontologists have uncovered clues indicating that certain dinosaurs traveled long distances in response to changing environmental conditions and food availability. One compelling example comes from hadrosaurs, also known as duck-billed dinosaurs. Fossil discoveries in Alaska show that these herbivores lived in polar regions during warmer months, taking advantage of abundant vegetation. As winter approached and food became scarce, they likely migrated to more temperate areas. Sauropods, the long-necked giants of the dinosaur world, may have also been migratory. Studies of their teeth and bone composition suggest they moved between different feeding grounds throughout the year. This behavior would have allowed them to find fresh vegetation and avoid overgrazing in any single area. However, not all dinosaurs were migratory. Many species, particularly smaller ones, likely remained in the same general area year-round, adapting to seasonal changes in their local environment. The diversity of dinosaur lifestyles reflects the complex ecosystems of the Mesozoic era, with different species evolving various strategies to survive and thrive in their respective habitats. The geography of prehistoric Earth played a crucial role in shaping dinosaur migration patterns. During the Mesozoic era, when dinosaurs roamed the planet, the continents were arranged differently than they are today. This unique layout of land and sea created various pathways and barriers that influenced how dinosaurs moved across the landscape. Large land masses like Pangaea and later Laurasia and Gondwana provided extensive corridors for dinosaur movement. These supercontinent configurations allowed for more widespread migration compared to our current, fragmented continental arrangement. As the continents slowly drifted apart, new seaways formed, creating obstacles that dinosaurs had to navigate around or adapt to. Mountain ranges and rivers also significantly impacted dinosaur migration. The formation of mountain chains like the early Rocky Mountains or the Appalachians created natural barriers, potentially isolating populations and influencing the direction of migratory routes. Rivers, on the other hand, often served as highways for dinosaur movement, providing water sources and lush vegetation along their banks. Climate zones, determined by latitude and geography, further shaped dinosaur migration patterns. Some species would move seasonally between warmer and cooler regions, following food sources or seeking more favorable breeding conditions. The interplay between changing geography and climate throughout the Mesozoic era continually reshaped these migratory routes, driving dinosaur adaptation and evolution over millions of years. Fossil distributions provide valuable insights into dinosaur migration patterns, offering a window into the ancient world of these fascinating creatures. By examining where dinosaur remains are found across different geographical locations and geological time periods, paleontologists can piece together evidence of their movements and behaviors. One key aspect that fossil distributions reveal is the existence of dinosaur highways, ancient routes that various species used for seasonal migrations. These pathways, often following coastlines or river valleys, allowed dinosaurs to move between feeding grounds and nesting sites. For example, fossil evidence suggests that some hadrosaurs, or duck-billed dinosaurs, migrated thousands of kilometers annually between what is now Alaska and Alberta, Canada. Fossil distributions also help scientists understand how dinosaurs adapted to changing climates and environments over time. As land masses shifted and climates fluctuated, dinosaur species had to move to survive. The presence of similar fossils on continents that are now separated by oceans provides evidence of these long-term migrations and the connections between ancient landmasses. Moreover, studying fossil distributions allows researchers to identify patterns of dinosaur diversity and population density in different regions. This information helps paint a picture of dinosaur ecosystems, showing which areas were most hospitable to certain species and how different dinosaur groups interacted and competed for resources as they moved across the landscape. Climate change played a significant role in shaping dinosaur migration patterns throughout their long reign on Earth. As temperatures fluctuated and environments shifted, dinosaurs adapted by moving to more favorable habitats. During warmer periods, many species expanded their ranges towards the poles, while cooler times saw them retreat towards the equator. These climate-driven migrations led to the evolution of new species as dinosaurs encountered different ecosystems and food sources. Some herbivorous dinosaurs, like the long-necked sauropods, likely followed seasonal patterns of plant growth, moving to find fresh vegetation as the climate changed. This behavior would have influenced the movements of their predators as well. Evidence from fossil discoveries suggests that some dinosaurs undertook long-distance migrations. For instance, trackways found in Alaska indicate that hadrosaurs, also known as duck-billed dinosaurs, traveled thousands of kilometers annually to escape harsh winter conditions. These journeys would have required significant energy expenditure and coordination among herds. As the climate continued to change over millions of years, some dinosaur species found themselves unable to adapt quickly enough. This led to localized extinctions and shifts in ecosystem dynamics. The ability or inability to migrate in response to climate change ultimately played a crucial role in determining which dinosaur species survived and thrived, and which ones faced decline or extinction. Flying and marine reptiles from ancient times indeed engaged in migration, much like many modern animals do today. Pterosaurs, the flying reptiles that dominated the skies during the age of dinosaurs, likely undertook seasonal journeys across vast distances. Evidence suggests they traveled between feeding grounds and nesting sites, possibly following food sources or seeking more favorable climates. In the oceans, various marine reptiles exhibited migratory behaviors. Plesiosaurs, with their long necks and powerful flippers, are thought to have made long-distance trips across ancient seas. These journeys may have been tied to breeding cycles or changes in ocean temperatures and food availability. Ichthyosaurs, dolphin-like reptiles, also showed signs of migratory patterns, possibly following schools of fish or squid across different marine regions. Mosasaurs, large predatory marine lizards, likely undertook seasonal migrations as well. As apex predators, they would have followed the movements of their prey, which in turn responded to changes in water temperature and nutrient availability. These migrations helped maintain the balance of marine ecosystems and allowed these reptiles to exploit different food sources throughout the year. Fossil evidence, including bone structures and chemical signatures, provides clues about these ancient migrations. By studying these patterns, scientists gain insights into the behavior and ecology of extinct species, as well as the environmental conditions that shape their movements across prehistoric skies and seas. Dinosaur parenting strategies varied widely across different species, reflecting the diverse nature of these ancient creatures. Some dinosaurs, particularly among the large sauropods, likely laid their eggs and left them to fend for themselves. This hands-off approach was similar to that of modern-day sea turtles or crocodiles. In contrast, many theropod dinosaurs, including the ancestors of modern birds, showed remarkable parental care. Fossils have revealed nests where adult dinosaurs were found sitting atop their eggs, suggesting they incubated them much like birds do today. Some species, such as Oviraptor, were even fossilized in brooding positions, protecting their nests from sandstorms or predators. Evidence suggests that some dinosaur species formed family groups or even herds to protect their young. Maiasaura, whose name means good mother lizard, left behind fossils indicating they cared for their offspring in large nesting colonies. These dinosaurs likely brought food to their nest-bound young and protected them from predators. Perhaps most intriguingly, recent studies of dinosaur growth rates suggest that some species, particularly among the larger carnivores, may have cared for their young for extended periods. This prolonged parental care would have allowed juvenile dinosaurs to learn crucial survival skills before venturing out on their own, much like modern apex predators such as lions or wolves. Fossilized nests provide invaluable insights into dinosaur parenting behaviors, offering a window into the lives of these ancient creatures. These preserved remnants reveal that many dinosaur species were attentive parents, much like modern birds. The size, shape, and arrangement of eggs in these nests can tell us about clutch sizes and how dinosaurs organized their nesting sites. Some fossilized nests show evidence of adult dinosaurs incubating their eggs, suggesting they used body heat to keep their offspring warm. This behavior is similar to that of present-day birds and indicates a level of parental care previously unknown in dinosaurs. In certain species, scientists have found multiple generations of eggs in the same nest, hinting at the possibility of parents returning to the same nesting grounds year after year. Trace fossils around nests, such as footprints or tail drag marks, offer clues about how adult dinosaurs moved and behaved around their eggs. These markings can indicate whether parents stood guard over their nests or how frequently they visited to tend to their eggs. In some cases, fossilized nests have been found with the remains of juvenile dinosaurs still inside, suggesting that some species cared for their young even after hatching. The study of fossilized nests has also revealed surprising diversity in dinosaur reproductive strategies. Some species laid many small eggs, while others produced fewer, larger eggs. This variation likely reflects different approaches to ensuring the survival of offspring, balancing factors such as predation risk and resource availability. By examining these ancient nurseries, paleontologists continue to uncover new details about the complex social behaviors and family lives of dinosaurs, challenging our perceptions of these fascinating creatures. Fossil evidence suggests that some dinosaur species did indeed exhibit communal nesting behaviors. This fascinating aspect of dinosaur life provides insights into their social structures and parenting strategies. One of the most well-documented examples comes from the Cretaceous period, involving a group of duck-billed dinosaurs called Maiasaura. At a site in Montana, paleontologists discovered numerous nests arranged in a pattern that strongly indicates these dinosaurs nested in large colonies. Each nest contained up to 25 eggs, and the proximity of the nests suggests these dinosaurs lived and raised their young in social groups. Similar evidence has been found for other dinosaur species. Protoceratops, a smaller relative of the famous Triceratops, left behind fossilized nests in Mongolia that were closely spaced, indicating they too may have engaged in communal nesting. Even some theropods, the group that includes carnivorous dinosaurs like Tyrannosaurus rex, showed signs of this behavior. Fossil sites in Argentina have revealed multiple nests of the theropod Musaurus patagonicus arranged in a way that suggests cooperative breeding. These communal nesting behaviors likely offered several advantages. Group living could have provided better protection against predators, allowed for shared care of offspring, and potentially facilitated more efficient foraging. This evidence challenges earlier notions of dinosaurs as solitary creatures and paints a picture of complex social interactions among these ancient animals. Dinosaur parenting varied greatly across different species, much like we see in modern animals. Some dinosaurs provided extensive care for their young, while others left their offspring to fend for themselves shortly after hatching. Evidence from fossilized nests and young dinosaurs suggests that many species, particularly among the bird-like theropods, were attentive parents. For instance, oviraptorosaurs and troodontids likely sat on their nests to incubate eggs, similar to modern birds. This behavior indicates a significant investment in offspring care even before hatching. After hatching, some dinosaur species continued to care for their young for extended periods. Maiasaura, whose name means good mother lizard, is believed to have cared for its offspring in large nesting colonies for months or even years. Fossil evidence shows that young Maiasaura remained in the nest while their leg bones developed, suggesting they were fed by their parents during this time. However, not all dinosaurs were devoted parents. Some species, particularly among the larger sauropods, likely laid many eggs and provided little to no parental care. These dinosaurs may have relied on a strategy of producing numerous offspring, with the expectation that a few would survive to adulthood without parental involvement. This diversity in parenting strategies reflects the complex and varied lives of dinosaurs across their long reign on Earth. Dinosaur eggs were remarkable structures that protected and nourished developing embryos millions of years ago. These eggs varied in size and shape depending on the species, ranging from as small as a chicken egg to as large as a football. The outer shell of dinosaur eggs was made primarily of calcium carbonate, similar to modern bird eggs, but often thicker and more durable to withstand the harsh prehistoric environments. The internal structure of dinosaur eggs was complex, featuring several distinct layers. Beneath the hard outer shell was a membrane that helped regulate gas exchange and moisture retention. Inside this membrane, the embryo developed surrounded by nutrient-rich fluids and yolk. Some dinosaur eggs had porous shells that allowed for better gas exchange, while others had smoother surfaces that may have helped prevent water loss in arid climates. Paleontologists have discovered fascinating details about dinosaur eggs through careful study. Some eggs contained intricate networks of blood vessels, suggesting that dinosaur embryos were well supplied with oxygen and nutrients during development. In certain species, the inner surface of the eggshell had unique ridges or textures that may have helped the baby dinosaur break out when it was ready to hatch. The arrangement of dinosaur eggs in nests also provides valuable insights into dinosaur behavior. Some species laid their eggs in neat circular patterns, while others scattered them more randomly. This variety in nesting strategies offers clues about parental care and breeding habits among different dinosaur groups, painting a vivid picture of life in the Mesozoic era. Nesting behaviors in animals have evolved over millions of years, driven by the need for protection, reproduction, and offspring care. This fascinating aspect of animal behavior can be traced back to the earliest terrestrial vertebrates, which began to lay their eggs on land. As animals moved from water to land, they faced new challenges in protecting their offspring. The development of amniotic eggs, which could survive outside of water, was a crucial step. These eggs required a safe place for incubation, leading to the emergence of basic nesting behaviors. Over time, nesting behaviors became more complex and diverse. Birds, in particular, developed elaborate nest-building techniques using a variety of materials. Some construct intricate woven structures, while others create simple scrapes in the ground. This diversity reflects the different environmental pressures and survival strategies of various species. Mammals also evolved nesting behaviors, albeit in different forms. From the complex tunnel systems of prairie dogs to the leafy nests of gorillas, these behaviors serve to protect offspring and provide a safe space for early development. The evolution of nesting behaviors demonstrates how animals have adapted to their environments, balancing the needs for protection, temperature regulation, and camouflage to ensure the survival of their young. Brood parasitism, a reproductive strategy where animals lay their eggs in the nests of other species, is well documented in modern birds. However, evidence for this behavior in dinosaurs is limited and largely speculative. While we cannot definitively say that no dinosaurs practiced brood parasitism, there is currently no concrete fossil evidence to support this idea. Paleontologists have made significant discoveries about dinosaur nesting behaviors, including communal nesting sites and evidence of parental care. Many dinosaur species, particularly among the theropods and ornithischians, built nests and cared for their young. This level of parental investment suggests that most dinosaurs were likely not brood parasites. However, the diversity of dinosaur species and their reproductive strategies was vast. Some smaller theropod dinosaurs, particularly those closely related to birds, might have experimented with various reproductive techniques, potentially including brood parasitism. The challenge lies in finding fossil evidence that would conclusively demonstrate this behavior. As our understanding of dinosaur behavior continues to evolve, future discoveries may shed light on this intriguing question. For now, brood parasitism remains a fascinating behavior observed in modern birds, but its presence in their dinosaur ancestors remains a mystery. Herbivores and carnivores developed distinct nesting strategies over millions of years of evolution, adapting to their specific ecological niches and survival needs. Herbivorous dinosaurs, particularly the large sauropods and hadrosaurs, often engaged in colonial nesting behaviors. These creatures would gather in vast numbers to create extensive nesting grounds, laying hundreds or even thousands of eggs in a single area. This strategy offered safety in numbers, as the sheer quantity of adults could better protect their offspring from predators. In contrast, carnivorous dinosaurs typically adopted more solitary nesting habits. Theropods, such as the fearsome Tyrannosaurus rex, would often select secluded locations for their nests away from other members of their species. This approach helped prevent cannibalism of their young, a behavior observed in some modern reptiles. Carnivores also tended to lay fewer eggs than their herbivorous counterparts, investing more energy in the care and protection of each individual offspring. The structure of the nests themselves also differed between these two groups. Herbivores often created simple nest structures, sometimes just shallow depressions in the ground where they would lay their eggs. Some species, like certain duck-billed dinosaurs, might have covered their eggs with vegetation for incubation. Carnivorous dinosaurs, on the other hand, often constructed more elaborate nests. Some theropods built nests similar to those of modern crocodiles, using mounds of vegetation that would generate heat as they decomposed, helping to incubate the eggs. These diverse nesting strategies reflect the different challenges faced by herbivores and carnivores in the ancient world. While herbivores relied on strength in numbers and high reproductive rates to ensure the survival of their species, carnivores focused on careful placement and protection of fewer offspring. These adaptations played a crucial role in the success and diversity of dinosaur species throughout the Mesozoic era. Fossilized dinosaur embryos offer a treasure trove of information about these ancient creatures. These rare and delicate fossils provide unique insights into dinosaur development, behavior, and evolution that we cannot glean from adult specimens alone. By studying the bones and tissues of unhatched dinosaurs, scientists can determine how quickly these animals grew inside their eggs and how their body structures developed over time. This information helps paleontologists understand the growth rates of different dinosaur species and compare them to modern reptiles and birds. Embryonic fossils also reveal details about dinosaur reproductive strategies. The arrangement of eggs in nests and the development stage of the embryos when fossilized can indicate how dinosaurs cared for their young. Some fossils have shown that certain species may have exhibited parental care, similar to modern birds. Perhaps most intriguingly, dinosaur embryos provide clues about the evolutionary link between dinosaurs and birds. Features such as tooth formation, skull shape, and limb development in embryonic fossils help scientists trace the gradual changes that occurred as some dinosaur lineages evolved into the birds we see today. These minute details preserved in fossilized embryos continue to reshape our understanding of dinosaur biology and their place in the evolutionary timeline of life on Earth. Dinosaur nesting behavior shared similarities with both modern birds and reptiles, reflecting their evolutionary position between these two groups. Like many reptiles, some dinosaurs buried their eggs in soil or vegetation mounds, using the warmth of decomposition to incubate their offspring. However, evidence suggests that certain dinosaur species, particularly theropods closely related to birds, exhibited more advanced nesting behaviors. Fossil discoveries have revealed that some dinosaurs, such as oviraptors and troodontids, arranged their eggs in circular patterns within nests, similar to modern birds. These nests were often open, allowing the parent dinosaurs to sit directly on the eggs, providing body heat and protection. This behavior is strikingly similar to that of present-day avian species and represents a key evolutionary step towards modern bird nesting. Interestingly, some dinosaurs appear to have practiced nest site fidelity, returning to the same nesting grounds year after year. This behavior is observed in both modern reptiles and birds. Paleontologists have also found evidence of colonial nesting in certain dinosaur species, where multiple individuals nested in close proximity, a strategy employed by many contemporary birds for protection against predators. The diversity of dinosaur nesting strategies underscores the complex and varied reproductive behaviors of these ancient creatures. From simple buried nests to more elaborate open constructions, dinosaur nesting practices bridge the gap between reptilian and avian approaches, providing crucial insights into the evolutionary journey from reptiles to birds. Dinosaurs exhibited a wide range of running speeds, varying greatly depending on their species, size, and body structure. The fastest dinosaurs were likely small, agile theropods like Compsognathus and Velociraptor. These swift predators could potentially reach speeds of up to 40 miles per hour, comparable to modern-day ostriches. Larger theropods such as Tyrannosaurus rex, contrary to popular depictions, were not built for high-speed chases. Recent studies suggest that T-Rex probably moved at a more modest pace, with top speeds estimated between 10 to 20 miles per hour. Their massive size and weight made rapid acceleration and sharp turns challenging. Herbivorous dinosaurs also showed diverse running capabilities. Smaller, more nimble plant eaters like Hypsilophodon could likely sprint at speeds of 25 miles per hour or more when evading predators. In contrast, enormous sauropods such as Brachiosaurus and Diplodocus were not built for speed, moving at slower walking paces of perhaps 5 to 10 miles per hour. Paleontologists determine these speed estimates through various methods, including analyzing fossilized footprints, studying bone structure and muscle attachment sites, and using computer simulations. While we cannot observe dinosaurs in motion, these scientific approaches help us paint a clearer picture of how these ancient creatures moved through their prehistoric environments. Scientists employ several ingenious methods to estimate how fast dinosaurs could move, despite these creatures having been extinct for millions of years. One approach involves analyzing fossilized footprints and trackways. By measuring the distance between footprints and the length of the dinosaur's stride, researchers can calculate its speed at the time the tracks were made. This method provides valuable insights into the actual speeds at which these ancient animals traveled in specific instances. Another technique examines the structure of dinosaur bones and muscles. By studying the size and shape of leg bones, scientists can estimate the muscle mass and power output of a dinosaur's limbs. This information, combined with body mass estimates, allows researchers to model the potential running speeds of different species. Additionally, comparisons with modern animals of similar size and build help refine these estimates. Computer simulations have become an increasingly important tool in estimating dinosaur speeds. By creating detailed digital models of dinosaur skeletons and musculature, scientists can simulate how these animals might have moved. These models take into account factors such as weight distribution, joint flexibility, and energy efficiency to predict maximum running speeds and typical walking paces. Lastly, some researchers use a method called scaling, which compares the body proportions of dinosaurs to those of living animals. By examining how speed relates to size in modern species, scientists can make educated guesses about the locomotive capabilities of extinct dinosaurs. This approach helps validate and refine estimates derived from other methods, providing a more comprehensive understanding of dinosaur movement. Among the dinosaurs that roamed the Earth millions of years ago, several species were built for speed. The velociraptor, contrary to its portrayal in popular culture, was actually a relatively small dinosaur about the size of a turkey. Despite its modest size, it was incredibly quick and agile, estimated to reach speeds of up to 40 miles per hour. However, the true speed champions of the dinosaur world were likely the ornithomimids, often referred to as ostrich dinosaurs. These fleet-footed creatures, including species like Gallimimus and Struthiomimus, had long, powerful legs and a lightweight build that allowed them to achieve impressive velocities. Some paleontologists believe they could have reached speeds of up to 50 miles per hour, making them the cheetahs of the Cretaceous period. Another contender for the title of fastest dinosaur was the Compsognathus, a small theropod about the size of a chicken. Its lightweight frame and long legs suggest it was capable of rapid bursts of speed, possibly reaching up to 40 miles per hour. This nimble dinosaur would have been a formidable hunter of small prey and an expert at evading larger predators. It is important to note that these speed estimates are based on careful analysis of fossil evidence, including leg bone proportions, muscle attachment sites, and comparisons with modern animals. While we cannot observe these ancient creatures in motion, the study of their anatomy provides valuable insights into their locomotive abilities, helping us piece together a picture of life in the age of dinosaurs. The size of a dinosaur played a crucial role in determining its speed and overall mobility. Generally, smaller dinosaurs were faster and more agile than their larger counterparts. This relationship between size and speed is rooted in fundamental principles of physics and biology. Smaller dinosaurs, like the swift Compsognathus, which was about the size of a chicken, could reach impressive speeds. Their lightweight bodies and long, slender legs allowed for quick acceleration and nimble movements. These adaptations made them excellent hunters of small prey and helped them evade larger predators. On the other hand, massive dinosaurs like the Brachiosaurus faced more challenges when it came to speed. Their enormous body mass required tremendous amounts of energy to move, and their bone structure had to be robust enough to support their weight. This resulted in slower, more lumbering movements. However, these giants had other advantages, such as reach and defensive capabilities, that compensated for their lack of speed. Interestingly, some large dinosaurs evolved specific adaptations to enhance their speed despite their size. The Tyrannosaurus rex, for instance, had powerful leg muscles and a stiff tail that acted as a counterbalance, allowing it to move faster than one might expect for its size. This combination of features enabled it to be an effective predator despite its massive build. Several dinosaur species were built for speed, with some capable of impressive bursts of acceleration and sustained running. The velociraptor, contrary to its portrayal in popular media, was actually a relatively small dinosaur about the size of a turkey. However, it was likely quite agile and could reach speeds of up to 30 miles per hour in short sprints. For sustained high-speed running, we turn to larger theropods like the Tyrannosaurus rex. Recent studies suggest that despite its massive size, the T-Rex could maintain speeds of about 12 to 18 miles per hour over longer distances. This is comparable to the pace of a human long-distance runner. One of the most impressive runners among dinosaurs was likely the Ornithomimus, often called the ostrich mimic dinosaur. With its long, powerful legs and lightweight frame, the Ornithomimus was built for speed and endurance. Scientists estimate it could have maintained speeds of up to 30 miles per hour for extended periods, making it one of the fastest known dinosaurs. The Gallimimus, another ostrich-like dinosaur, was also an exceptional runner. Its fossilized remains show adaptations for speed and agility, including hollow bones to reduce weight and strong leg muscles for powerful strides. These features allowed the Gallimimus to likely achieve and maintain speeds similar to those of the Ornithomimus, making it well equipped for both escaping predators and chasing down prey. Dinosaur leg structure played a crucial role in determining their speed and overall mobility. The arrangement of bones, muscles, and joints in their legs varied greatly among different species, resulting in a wide range of locomotion capabilities. For many theropod dinosaurs, like the famous Tyrannosaurus rex, their long, powerful hind legs were built for speed and agility. These legs featured strong muscles and lightweight bones, allowing for quick acceleration and high-speed pursuits. The positioning of their legs directly under their bodies, similar to modern birds, provided excellent balance and efficient movement. In contrast, larger sauropods like Brachiosaurus had thick, pillar-like legs designed to support their massive body weight. While these legs were incredibly strong, they were not built for speed. Instead, they allowed these giant herbivores to move steadily across vast distances in search of food. Some dinosaurs, such as the swift-footed Velociraptor, had specialized adaptations in their leg structure. Their legs featured a distinctive sickle-shaped claw on the second toe, which they could raise off the ground while running. This adaptation, combined with their lightweight build and long, stiff tail for balance, made them exceptionally fast and agile predators. Fossil trackways provide invaluable insights into dinosaur locomotion, offering a window into the past that allows paleontologists to estimate how fast these ancient creatures moved. By examining the spacing, depth, and pattern of footprints preserved in rock, scientists can deduce crucial information about dinosaur gaits and speeds. The distance between individual footprints in a trackway reveals the stride length of the dinosaur. Longer strides generally indicate faster movement, while shorter steps suggest a slower pace. Additionally, the depth of the footprints can indicate the weight distribution and force applied during locomotion, providing clues about whether the animal was walking, trotting, or running. Paleontologists use sophisticated biomechanical models to analyze these trackways, comparing them to the locomotion patterns of modern animals. This approach allows researchers to estimate the hip height of the dinosaur and calculate its velocity based on the relationship between leg length and stride. Some trackways have revealed that certain dinosaur species could reach impressive speeds, with some theropods potentially achieving speeds of up to 40 kilometers per hour. However, trackways also show that many dinosaurs, particularly larger species, moved at more modest speeds most of the time. This information helps scientists understand dinosaur behavior, energy expenditure, and even hunting strategies. By combining trackway data with other fossil evidence, researchers continue to refine our understanding of how these magnificent creatures moved through their ancient environments. Speed played a crucial role in the complex predator-prey dynamics of dinosaur ecosystems. Swift predators like Velociraptor relied on their agility and speed to chase down smaller, nimble prey. These quick hunters could reach speeds of up to 40 miles per hour in short bursts, allowing them to close the distance on their targets rapidly. Conversely, larger predators such as Tyrannosaurus rex were not built for sustained high-speed chases. Instead, they used powerful legs to achieve quick acceleration, surprising their prey with sudden bursts of speed. This strategy was particularly effective against larger, slower herbivores that couldn't outrun them over short distances. Herbivorous dinosaurs evolved various adaptations to counter the threat of fast predators. Some, like Gallimimus, developed long, slender legs for swift escape. Others, such as the massive sauropods, relied on their sheer size and strength rather than speed to deter attackers. Smaller plant eaters often formed herds, using their collective vigilance and the confusion created by their numbers to evade swift predators. The importance of speed in these prehistoric ecosystems led to an evolutionary arms race. Over millions of years, both predators and prey continually adapted, developing more efficient locomotion and enhanced sensory capabilities. This ongoing competition shaped the diverse array of dinosaur species that dominated the Earth for over 160 million years. Flying dinosaurs, more accurately known as pterosaurs, were remarkably adapted for both ground movement and aerial locomotion. However, their speed capabilities differed significantly between these two modes of travel. In the air, pterosaurs were incredibly efficient flyers. Their hollow bones and membranous wings allowed them to soar and glide with great ease. Some species, like the giant Quetzalcoatlus, could potentially reach speeds of up to 100 kilometers per hour during flight. This impressive aerial velocity allowed them to cover vast distances and hunt effectively from the skies. On the ground, pterosaurs were not as swift. While they could walk and run on all fours, their limb structure was primarily adapted for launching into flight and landing. Most pterosaurs likely moved at speeds comparable to modern birds on the ground, which typically range from 5 to 15 kilometers per hour. Larger pterosaurs might have been even slower due to their size. Considering these factors, it is clear that pterosaurs were generally faster in the air than on the ground. Their aerial speed not only surpassed their terrestrial capabilities, but also allowed them to outpace many of their contemporaries, making them formidable predators and efficient long-distance travelers in the skies of the Mesozoic era. Depictions of dinosaur speed in popular media often exaggerate or oversimplify the reality of how these ancient creatures moved. Many films and television shows portray large predatory dinosaurs like Tyrannosaurus rex as capable of chasing down prey at high speeds, but scientific evidence suggests a different picture. Research into dinosaur locomotion indicates that many large theropods, including Tyrannosaurus, were likely not as fast as commonly depicted. Studies of leg bone structure, muscle attachment sites, and estimated body mass suggest that these animals probably had a top speed of around 20 to 25 miles per hour. This is considerably slower than many popular portrayals, though still impressive for an animal of that size. Smaller dinosaurs, particularly some of the bird-like theropods, were likely much faster and more agile. Velociraptors, for instance, are often shown as swift hunters, which is more accurate to their probable capabilities. However, media depictions frequently overlook the diversity of dinosaur species and their varied locomotion styles, from the lumbering gait of large sauropods to the more nimble movements of smaller herbivores. Ultimately, while popular media has made strides in updating dinosaur depictions based on new scientific findings, the need for dramatic action often leads to exaggerated portrayals of dinosaur speed and agility. The reality of dinosaur locomotion was likely more diverse and nuanced than what we typically see on screen. Dinosaurs were primarily land-dwelling creatures, but some species adapted to life in and around water. However, there were no fully aquatic dinosaurs in the same way that whales or dolphins are aquatic mammals today. The animals often mistaken for aquatic dinosaurs were actually marine reptiles, which were not dinosaurs at all. These marine reptiles included groups like plesiosaurs, ichthyosaurs, and mosasaurs. They lived alongside dinosaurs during the Mesozoic era, but evolved from different reptilian ancestors. These creatures were fully adapted to aquatic life, with streamlined bodies, flippers, and in some cases, fins. While not dinosaurs, some true dinosaurs did spend considerable time in water. Spinosaurus, for example, is now believed to have been semi-aquatic. Recent fossil evidence suggests it had dense bones and a paddle-like tail, adaptations that would have helped it swim and hunt fish in rivers and coastal areas. Other dinosaurs like Baryonyx and Suchomimus also showed adaptations for a partially aquatic lifestyle, with crocodile-like snouts and claws well suited for catching fish. These dinosaurs likely spent much of their time in or near water, but they were not fully aquatic in the way that the marine reptiles were. Throughout their long reign on Earth, dinosaurs evolved to thrive in diverse environments, including water. Some dinosaurs adapted to semi-aquatic lifestyles, developing unique features that allowed them to navigate both land and aquatic habitats with ease. One notable example is Spinosaurus, a massive predator that lived during the Cretaceous period. This dinosaur evolved a long, crocodile-like snout filled with conical teeth, perfect for catching slippery fish. Its powerful forelimbs and large, paddle-like feet helped it swim efficiently. Perhaps most striking was its sail-like structure on its back, which may have aided in temperature regulation or served as a display feature while in the water. Other dinosaurs, like the duck-billed hadrosaurs, also showed adaptations for a semi-aquatic lifestyle. These herbivores had wide, flattened snouts that could have been used to forage for aquatic plants. Their strong tails and webbed feet suggest they were capable swimmers, allowing them to escape predators by retreating into the water. Some dinosaurs even developed more extreme aquatic adaptations. Halscaraptor, a small theropod, had a long, flexible neck similar to modern waterfowl and flipper-like forelimbs that would have been more suited for swimming than walking. These adaptations showcase the remarkable diversity and evolutionary flexibility of dinosaurs as they conquered various ecological niches, including those straddling the boundary between land and water. Paleontologists have uncovered several compelling pieces of evidence that suggest some dinosaurs were indeed capable swimmers. Fossil remains of certain dinosaur species show adaptations that would have been beneficial for life in and around water. For instance, the Spinosaurus, a large carnivorous dinosaur, had dense bones and a crocodile-like snout, features that would have aided in swimming and hunting aquatic prey. Fossilized footprints discovered in riverbeds and lake bottoms provide further evidence of dinosaurs traversing through water. These trace fossils, known as swim tracks, show the claw marks of dinosaurs as they pushed off the bottom of shallow bodies of water. Such tracks have been found for various dinosaur species, indicating that swimming was not limited to just a few specialized types. The discovery of aquatic plant material in the stomach contents of some fossilized dinosaurs also supports the idea of swimming behavior. This suggests that these dinosaurs were foraging in water deep enough to require swimming. Additionally, the presence of certain dinosaur fossils in ancient marine sediments indicates that some species may have ventured far from shore, either intentionally or by accident. Recent studies of dinosaur lung structure and ribcage flexibility have revealed similarities to modern diving birds, suggesting that some dinosaurs may have been capable of staying submerged for extended periods. This adaptability would have been advantageous for hunting aquatic prey or escaping terrestrial predators, further supporting the concept of swimming dinosaurs. Aquatic adaptations in dinosaurs were remarkably similar to those seen in modern animals, showcasing the power of convergent evolution. Many dinosaur species developed streamlined bodies, paddle-like limbs, and long necks, mirroring adaptations found in today's marine reptiles and mammals. Plesiosaurs, for instance, evolved flippers that closely resemble those of sea turtles and penguins. These flat, elongated limbs provided efficient propulsion through water, allowing the animals to navigate their aquatic environment with ease. Similarly, the long, flexible necks of elasmosaurids served a comparable function to those of modern-day swans, enabling them to reach food in various directions while keeping their bodies stable. Ichthyosaurs took aquatic adaptation even further, developing a body shape strikingly similar to modern dolphins and sharks. Their streamlined form, dorsal fins, and powerful tails allowed for swift movement through water, much like their contemporary counterparts. This remarkable similarity in body plan, despite millions of years of separate evolution, underscores the effectiveness of these adaptations for aquatic life. However, one key difference lies in breathing mechanisms. While modern marine mammals like whales and dolphins evolved blowholes, aquatic dinosaurs retained more traditional nostrils. This difference reflects the distinct evolutionary paths taken by these groups in adapting to life in water, highlighting the diverse solutions nature can produce to similar environmental challenges. Many dinosaurs adapted to diverse environments and food sources, including aquatic habitats. One notable group that specialized in fishing was the Spinosaurids. These large theropod dinosaurs evolved unique features that made them adept at catching fish and other aquatic prey. Spinosaurus, the most famous member of this group, had a long, crocodile-like snout filled with conical teeth perfect for grasping slippery fish. Its nostrils were positioned high on its skull, allowing it to breathe while partially submerged. The Spinosaurids also had powerful forelimbs with curved claws, useful for hooking and holding onto their aquatic meals. Recent fossil evidence suggests that Spinosaurus had dense bones and a paddle-like tail, indicating it was likely semi-aquatic and spent considerable time in the water. This adaptation would have given it a significant advantage when hunting fish in rivers and coastal areas during the Cretaceous period, around 100 million years ago. While Spinosaurids were the most specialized dinosaurs for fishing, other theropods like Baryonyx and Suchomimus also showed adaptations for a fish-based diet. These fascinating creatures demonstrate the incredible diversity of dinosaur species and their ability to exploit various ecological niches, including aquatic environments. Dinosaurs and marine reptiles coexisted during the Mesozoic era, but they generally occupied different ecological niches. While dinosaurs were primarily terrestrial animals, some species adapted to semi-aquatic lifestyles and competed with marine reptiles in coastal and shallow water environments. One notable group of dinosaurs that ventured into aquatic habitats was the Spinosaurids. These large theropods, including Spinosaurus and Baryonyx, had elongated snouts filled with conical teeth similar to those of modern crocodiles. This adaptation allowed them to catch fish and other aquatic prey effectively. Fossil evidence suggests that Spinosaurids spent significant time in and around water, potentially competing with smaller marine reptiles for food resources. Another group of dinosaurs that interacted with marine environments was the duck-billed hadrosaurs. While not truly aquatic, these herbivores often lived near coastal areas and wetlands. Their wide, flat beaks were well suited for browsing on aquatic vegetation, bringing them into potential conflict with some marine reptiles that fed on similar plants. However, it is important to note that true marine reptiles, such as plesiosaurs, ichthyosaurs, and mosasaurs, were far better adapted to fully aquatic lifestyles than any dinosaur. These reptiles dominated the open oceans and deep waters where dinosaurs could not compete. The competition between dinosaurs and marine reptiles was largely limited to shorelines and shallow waters where their habitats overlapped. Fossil footprints provide invaluable insights into dinosaur behavior, including their ability to wade or swim. These preserved tracks offer a unique window into the past, allowing paleontologists to study dinosaur movements in aquatic environments. When dinosaurs walked through shallow water or along shorelines, their footprints were often preserved in soft sediment. The depth and shape of these impressions can reveal important information about how dinosaurs interacted with water. Shallow, well-defined prints suggest wading behavior, while deeper, more distorted tracks might indicate swimming or floating. Some fossil trackways show a transition from walking to swimming, with footprints becoming progressively fainter and more widely spaced. This pattern indicates that the dinosaur was gradually losing contact with the bottom as the water deepened. In certain cases, only claw marks are visible, suggesting the animal was paddling or using its limbs to propel itself through deeper water. Fossil footprints have also revealed unexpected swimming abilities in some dinosaur species. Trackways found in China, for example, suggest that some theropod dinosaurs were capable of moving through water using a kick-swimming motion similar to modern birds. These discoveries challenge previous assumptions about dinosaur locomotion and expand our understanding of their ecological roles in ancient aquatic ecosystems. Dinosaurs primarily evolved as land-dwelling creatures, but several lineages developed fascinating aquatic adaptations over millions of years. The most notable aquatic dinosaurs belong to the group called Spinosaurids, which included species like Spinosaurus and Baryonyx. These theropods evolved elongated snouts filled with conical teeth, perfect for catching slippery fish. Their nostrils moved higher on their skulls, allowing them to breathe while partially submerged. Spinosaurus took aquatic adaptations even further. Recent fossil discoveries reveal it had dense bones for buoyancy control and a paddle-like tail for propulsion through water. This made Spinosaurus the first known semi-aquatic dinosaur, capable of both swimming and walking on land. Its lifestyle was likely similar to modern crocodiles, spending much of its time in and around water. Other dinosaur groups also developed water-related adaptations. Some duck-billed hadrosaurs had webbed hands, suggesting they were skilled swimmers. Certain sauropods, like Brachiosaurus, might have waded in shallow waters, using their long necks to reach aquatic vegetation. These adaptations didn't make them fully aquatic, but allowed them to exploit watery environments for food and protection. It's important to note that while these dinosaurs had aquatic adaptations, they were distinct from the fully aquatic marine reptiles of their time, such as plesiosaurs and ichthyosaurs, which were not dinosaurs but separate reptile lineages that returned to the sea. Several dinosaur species thrived in swampy and marshy environments during the Mesozoic era. One of the most well-known examples is Spinosaurus, a massive carnivorous dinosaur that lived about 100 million years ago. Recent evidence suggests that Spinosaurus was well adapted for a semi-aquatic lifestyle, with dense bones for buoyancy control and a tail shape perfect for propulsion through water. Another dinosaur suited for marshy habitats was Baryonyx, a close relative of Spinosaurus. This theropod had a long, crocodile-like snout filled with conical teeth, ideal for catching slippery fish. Fossilized fish scales found in the stomach region of Baryonyx specimens provide strong evidence for its fish-eating habits. Herbivorous dinosaurs also made their homes in swampy areas. Parasaurolophus, a duck-billed hadrosaur, likely spent much of its time near water. Its distinctive hollow head crest may have served as a snorkel, allowing it to breathe while mostly submerged. Similarly, the long-necked sauropod Diplodocus might have waded in shallow swamps, using its elongated neck to reach vegetation in deeper waters. These adaptations highlight the diverse ways dinosaurs evolved to exploit different ecological niches, including the challenging yet resource-rich environments of swamps and marshes. Their ability to thrive in these habitats demonstrates the remarkable adaptability of dinosaurs throughout their long reign on Earth. Dinosaurs were primarily terrestrial animals, but some groups developed fascinating adaptations for aquatic environments. These adaptations played a significant role in expanding dinosaur diversity and driving their evolution into new ecological niches. One notable group of aquatic dinosaurs was the Spinosaurids, which included species like Spinosaurus. These carnivorous theropods evolved elongated snouts filled with conical teeth, perfect for catching slippery fish. Their nostrils moved higher on their skulls, allowing them to breathe while partially submerged. Some Spinosaurids even developed dense bones and powerful tails for swimming, enabling them to hunt effectively in water. Another group that ventured into aquatic habitats was the duck-billed hadrosaurs. While not fully aquatic, these herbivores likely spent considerable time in and around water. They evolved wide, flat beaks for browsing on aquatic vegetation and powerful tails that could have aided in swimming. This adaptation allowed them to exploit food sources unavailable to other herbivorous dinosaurs. These aquatic adaptations opened up new evolutionary pathways for dinosaurs. By moving into water-based environments, these species reduced competition with their terrestrial counterparts and accessed new food sources. This diversification contributed to the overall success and longevity of dinosaurs as a group, allowing them to thrive in a wider range of habitats across the planet. Dinosaurs exhibited a wide variety of diets, reflecting their diverse adaptations and ecological roles. Large herbivorous sauropods like Brachiosaurus and Diplodocus consumed vast quantities of plant matter, primarily ferns, cycads, and conifers. Their long necks allowed them to reach high into the tree canopies, accessing food sources unavailable to other species. In contrast, carnivorous theropods such as Tyrannosaurus rex and Allosaurus were fearsome predators. These meat-eaters hunted other dinosaurs and prehistoric animals, using their sharp teeth and powerful jaws to tear through flesh and bone. Some smaller theropods, like Compsognathus, likely supplemented their diet with insects and small vertebrates. Herbivorous ornithischians displayed a range of feeding strategies. Ceratopsians like Triceratops used their beaked mouths to crop low-growing vegetation, while hadrosaurs, such as Parasaurolophus, possessed complex dental batteries for grinding tough plant material. Stegosaurs and ankylosaurs, with their low-slung bodies, grazed on plants close to the ground. Some dinosaurs adapted to more specialized diets. Therizinosaurs, with their elongated claws and small heads, are thought to have been primarily herbivorous despite their theropod lineage. Others, like the small, bird-like oviraptor, may have been omnivorous, feeding on a mixture of plants, eggs, and small animals. Scientists employ various methods to uncover the dietary habits of dinosaurs that roamed the Earth millions of years ago. One key approach involves examining fossilized teeth, which provide crucial insights into what these ancient creatures ate. Sharp, serrated teeth often indicate a carnivorous diet, while flat, grinding teeth suggest a plant-based diet. The wear patterns on these teeth also offer clues, as different foods leave distinct marks. Fossilized stomach contents, though rare, provide direct evidence of a dinosaur's last meal. These precious finds can include plant material, bones, or even whole animals, painting a vivid picture of the dinosaur's diet. Coprolites, or fossilized feces, are another valuable source of information, containing undigested food particles that can be analyzed to determine dietary preferences. Modern technology has revolutionized the study of dinosaur diets. Chemical analysis of fossilized bones and teeth can reveal the presence of certain isotopes, indicating whether a dinosaur was primarily herbivorous or carnivorous. Additionally, computer simulations of dinosaur jaws and teeth help scientists understand how these animals processed their food, providing further insights into their dietary habits. Paleontologists also consider the broader ecological context when determining dinosaur diets. By studying the plants and other animals that existed in the same time and place as a particular dinosaur species, scientists can make informed inferences about potential food sources and predator-prey relationships. This holistic approach helps create a more comprehensive understanding of ancient ecosystems and the roles different dinosaurs played within them. Dinosaurs exhibited a wide range of dietary habits, and yes, some were indeed omnivorous. These versatile eaters consumed both plant matter and meat, adapting their diets based on food availability and environmental conditions. One well-known example is Ornithomimus, a swift-running dinosaur that lived during the late Cretaceous period. Its beak-like mouth was well-suited for a varied diet, allowing it to feed on plants, small animals, and even eggs. Another notable omnivorous dinosaur was Oviraptor, whose name ironically means egg thief. Initially thought to prey solely on eggs, further research revealed that its powerful beak could process both plants and small animals. This dietary flexibility likely gave omnivorous dinosaurs an advantage in changing environments, allowing them to survive on whatever food sources were available. Gallimimus, a close relative of Ornithomimus, is also believed to have been an omnivore. Its long neck and small head suggest it could browse on low-lying vegetation, while its speed and agility would have made it an effective hunter of small prey. These adaptable dinosaurs demonstrate that diverse feeding strategies were present even in the ancient world, challenging our perceptions of dinosaur diets. Dinosaur diets underwent significant changes throughout their long reign on Earth. Early dinosaurs, which appeared around 230 million years ago, were mostly small omnivores. These adaptable creatures could eat both plants and small animals, allowing them to thrive in various environments. As dinosaurs diversified, their diets became more specialized. Some lineages evolved into dedicated herbivores, developing complex digestive systems and specialized teeth for processing tough plant material. The long-necked sauropods, for instance, became efficient at consuming vast quantities of vegetation, fueling their massive bodies. Carnivorous dinosaurs also evolved, with some becoming apex predators. Theropods like Tyrannosaurus rex developed powerful jaws and sharp teeth, perfectly adapted for tearing through flesh and crunching bones. Meanwhile, other dinosaurs occupied unique dietary niches. Therizinosaurus, with its long claws, likely used them to pull down branches, becoming an herbivore despite its fearsome appearance. Towards the end of the dinosaur era, about 66 million years ago, flowering plants had become widespread. This led to further dietary adaptations among herbivorous dinosaurs, as they evolved to take advantage of these new food sources. The evolution of dinosaur diets reflects their remarkable ability to adapt to changing environments and exploit new ecological opportunities over millions of years. Coprolites provide paleontologists with valuable insights into the dietary habits of ancient creatures, including dinosaurs. These fossilized feces act as time capsules, preserving remnants of meals consumed millions of years ago. By examining the contents of coprolites, scientists can determine what dinosaurs ate and how their diets varied across species and environments. Coprolites often contain undigested plant material, such as seeds, leaves, and wood fragments. This evidence helps researchers identify the types of vegetation that made up herbivorous dinosaurs' diets. In some cases, coprolites have revealed surprising findings, such as grass-like plants in the feces of some dinosaurs, challenging previous assumptions about when certain plant species first evolved. For carnivorous dinosaurs, coprolites can contain fragments of bones, scales, and other animal remains. These fossils provide information about predator-prey relationships and hunting behaviors. By analyzing the size and composition of bone fragments, scientists can infer which animals were being consumed and how thoroughly they were processed during digestion. Coprolites also offer clues about dinosaur digestive systems and overall health. The presence of certain minerals or parasites in fossilized feces can indicate dietary deficiencies or diseases that affected these ancient creatures. This information helps paleontologists build a more comprehensive picture of dinosaur biology and ecology, shedding light on how these fascinating animals lived and interacted with their environment millions of years ago. Dinosaur tooth structure played a crucial role in their dietary habits, providing valuable insights into what these ancient creatures ate and how they lived. The shape, size, and arrangement of teeth in different dinosaur species were closely linked to their feeding strategies and food preferences. Carnivorous dinosaurs, such as Tyrannosaurus rex, possessed large, sharp, and serrated teeth. These blade-like structures were ideal for slicing through flesh and crushing bones. The teeth of these predators were often curved backward, helping to grip and hold onto struggling prey. In contrast, herbivorous dinosaurs like Triceratops had rows of smaller, leaf-shaped teeth designed for grinding tough plant material. Some dinosaurs, like Stegosaurus, had simple peg-like teeth suited for stripping leaves from branches. Others, such as the duck-billed hadrosaurs, developed complex dental batteries consisting of hundreds of teeth stacked together. This arrangement allowed for continuous replacement of worn teeth, enabling these dinosaurs to efficiently process large amounts of fibrous plant matter throughout their lives. By studying tooth wear patterns and analyzing fossilized tooth marks on bones, paleontologists can reconstruct the feeding behaviors and dietary preferences of different dinosaur species. This information helps paint a more complete picture of ancient ecosystems and the roles various dinosaurs played within them. Scientists have discovered evidence of filter-feeding dinosaurs, revealing a fascinating aspect of prehistoric life. These unique creatures belong to a group called ornithomimosaurs, often referred to as ostrich-mimic dinosaurs due to their resemblance to modern ostriches. One notable example is Gallimimus, a dinosaur that lived during the late Cretaceous period, approximately 70 million years ago. Fossil evidence suggests that Gallimimus had a specialized beak-like structure with comb-like projections, similar to those found in modern filter-feeding birds such as flamingos and ducks. This adaptation allowed Gallimimus to sift through water or mud, trapping small organisms and particles for consumption. By sweeping its head from side to side in shallow water, it could capture tiny aquatic creatures, algae, and other organic matter. This feeding strategy would have been particularly effective in wetland environments, where these dinosaurs likely spent much of their time. The discovery of filter-feeding dinosaurs highlights the diverse range of feeding strategies that evolved among these ancient creatures. It demonstrates how dinosaurs adapted to fill various ecological niches, much like modern animals do today. This finding also provides valuable insights into the complex ecosystems of the Cretaceous period and the evolutionary history of feeding mechanisms in vertebrates. Dinosaur diets played a crucial role in shaping their size and driving their evolution over millions of years. The diverse array of food sources available during the Mesozoic era allowed different dinosaur species to adapt and specialize, leading to an incredible variety of body shapes and sizes. Herbivorous dinosaurs, which fed on plants, often grew to enormous proportions. Their plant-based diets required them to consume vast quantities of vegetation to meet their nutritional needs. This led to the evolution of long necks in sauropods like Brachiosaurus, allowing them to reach high into the tree canopies for food. Their massive body size also helped them digest tough plant material more efficiently, as larger digestive systems could break down cellulose more effectively. Carnivorous dinosaurs, on the other hand, evolved to become efficient predators. Their meat-based diets provided more concentrated nutrients, allowing them to maintain smaller body sizes compared to their herbivorous counterparts. However, some carnivores like Tyrannosaurus rex still grew to impressive sizes, developing powerful jaws and sharp teeth to tackle large prey. The competition for food sources also drove evolutionary changes. As plant-eating dinosaurs developed defenses such as bony plates or spikes, carnivores evolved more sophisticated hunting strategies and stronger bite forces. This dietary arms race contributed to the incredible diversity of dinosaur species and their varying sizes throughout their reign on Earth. Diet played a crucial role in dinosaur competition and speciation, shaping the evolution and diversity of these ancient creatures over millions of years. As dinosaurs evolved, they developed specialized feeding strategies and adaptations that allowed them to exploit different food sources and ecological niches. Herbivorous dinosaurs, such as the long-necked sauropods and the armored stegosaurs, competed for plant resources. This competition led to the development of various adaptations, including different tooth structures and neck lengths, enabling them to access different types of vegetation. Some herbivores evolved to feed on low-lying plants, while others could reach leaves high in the tree canopy, reducing direct competition and promoting speciation. Carnivorous dinosaurs also faced intense competition for prey, driving the evolution of diverse hunting strategies and physical adaptations. Some became swift pursuit predators, while others developed powerful jaws and teeth for crushing bones. This specialization allowed different carnivorous species to coexist by targeting different prey or hunting in distinct ways. The interplay between herbivores and carnivores further influenced dinosaur evolution. As herbivores developed defensive features like armor or increased size, carnivores had to adapt their hunting techniques and physical attributes to overcome these defenses. This ongoing evolutionary arms race contributed to the remarkable diversity of dinosaur species that existed throughout the Mesozoic era. Our understanding of dinosaur diets has evolved significantly over the years, but it remains a complex area of study. Paleontologists use various methods to determine what dinosaurs ate, including analyzing fossilized teeth, jaw structures, and even preserved stomach contents. These methods have allowed us to make increasingly accurate assumptions about herbivorous and carnivorous dinosaurs. For herbivorous dinosaurs, we have strong evidence supporting our dietary assumptions. The flat, grinding teeth of many plant-eating dinosaurs, such as Triceratops and Stegosaurus, are clear indicators of their herbivorous nature. Additionally, fossilized plant material found in the stomach regions of some specimens provides direct evidence of their diets. However, the specific types of plants they consumed and their feeding behaviors are still subjects of ongoing research. Carnivorous dinosaurs present a more challenging case. While sharp, serrated teeth and powerful jaws strongly suggest a meat-based diet, the exact nature of their hunting and feeding habits is less certain. Recent studies have shown that some dinosaurs previously thought to be purely carnivorous may have had more varied diets, including some plant matter. This highlights the complexity of dinosaur diets and the need for continued research. It is important to note that our assumptions are continually refined as new evidence emerges. Advanced technologies, such as isotope analysis of fossilized bones and teeth, are providing more detailed insights into dinosaur diets. While our current understanding is more accurate than ever before, there is still much to learn about the dietary habits of these fascinating prehistoric creatures. Dinosaurs employed various strategies to regulate their body temperature, a topic that has fascinated paleontologists for decades. Recent research suggests that different dinosaur species used a mix of methods, challenging the traditional view of dinosaurs as purely cold-blooded or warm-blooded creatures. Many large dinosaurs likely maintained a constant body temperature through a process called gigantothermy. Their immense size allowed them to retain heat efficiently, much like modern-day elephants. This meant they could maintain a relatively stable internal temperature without the need for the rapid metabolism seen in mammals and birds. Smaller dinosaurs, on the other hand, may have relied more on behavioral adaptations to regulate their temperature. They might have basked in the sun to warm up or sought shade to cool down, similar to how modern reptiles behave. Some dinosaurs also had special adaptations like frills, plates, or sails that could have helped with temperature control by increasing surface area for heat exchange. Interestingly, evidence suggests that some dinosaur groups, particularly those closely related to birds, might have been truly warm-blooded. They likely had higher metabolic rates and could generate their own body heat, much like their avian descendants do today. This diversity in thermoregulation strategies across different dinosaur species highlights the complex and varied nature of these fascinating prehistoric creatures. Size played a crucial role in dinosaur thermoregulation, influencing how these ancient creatures regulated their body temperature. Larger dinosaurs, particularly the massive sauropods, benefited from a phenomenon known as gigantothermy. This concept suggests that their immense body mass helped them maintain a stable internal temperature. The sheer volume of a large dinosaur's body compared to its surface area meant it could retain heat more efficiently. This allowed them to stay warm even in cooler environments and reduce the energy needed for temperature regulation. Smaller dinosaurs, on the other hand, had a higher surface area to volume ratio, making them more susceptible to temperature fluctuations in their environment. Interestingly, some scientists propose that the long necks and tails of sauropods might have served as radiators, helping these giants dissipate excess heat when necessary. This adaptation would have been particularly useful in warmer climates or during periods of intense activity. The relationship between size and thermoregulation in dinosaurs provides insights into their behavior, habitat preferences, and evolutionary adaptations. It also helps explain how these remarkable creatures thrived in various environments for millions of years, showcasing the intricate ways in which biology and physics intersect in the natural world. Feathers and scales played crucial roles in temperature regulation for different groups of animals, each adapting to their specific environments. Feathers, found in birds and some dinosaurs, provide excellent insulation by trapping air close to the body. This air layer acts as a barrier against heat loss, helping birds maintain their high body temperatures even in cold environments. Feathers can also be adjusted to allow more or less air to be trapped, giving birds fine control over their body temperature. Scales, on the other hand, are found in reptiles and fish. For reptiles, scales help prevent water loss through the skin, which is essential for maintaining body temperature in hot, dry environments. The overlapping structure of scales creates a physical barrier that reduces evaporation. In some reptiles, scales can change color to absorb or reflect more sunlight, further aiding in temperature control. For fish, scales serve a different purpose in temperature regulation. They provide a protective layer that helps maintain the fish's internal temperature separate from the surrounding water. This is particularly important for species that live in environments with fluctuating temperatures. Both feathers and scales demonstrate how evolution has shaped animals to regulate their body temperature effectively in diverse habitats. These adaptations have allowed birds, reptiles, and fish to thrive in a wide range of environments, from the coldest polar regions to the hottest deserts, and from shallow streams to the depths of the ocean. Dinosaurs likely developed numerous behavioral adaptations for thermoregulation, allowing them to maintain optimal body temperatures in various environments. These ancient reptiles faced challenges similar to modern animals in regulating their internal heat, especially given the diverse climates they inhabited over millions of years. One probable adaptation was basking, where dinosaurs would have exposed themselves to direct sunlight to warm up. This behavior is common in modern reptiles and would have been particularly useful for dinosaurs in cooler climates or during colder seasons. Conversely, dinosaurs might have sought shade or water to cool down when temperatures rose too high, much like elephants and other large animals do today. Some dinosaur species may have engaged in seasonal migration, moving to more favorable climates as temperatures changed throughout the year. This behavior would have allowed them to avoid extreme cold or heat, ensuring access to suitable habitats and food sources year-round. Additionally, dinosaurs might have altered their activity patterns, becoming more active during cooler parts of the day in hot climates or warmer periods in colder regions. Evidence suggests that some dinosaurs may have used their body structures for thermoregulation. For instance, the large sail-like structures on the backs of dinosaurs, like Spinosaurus or Dimetrodon, might have served as heat-exchanging surfaces, allowing these animals to warm up or cool down more efficiently. While not strictly a behavior, the use of such adaptations would have influenced how these dinosaurs interacted with their environment to maintain optimal body temperatures. Climate played a crucial role in shaping the thermoregulation strategies of dinosaurs throughout their long reign on Earth. As the climate fluctuated over millions of years, dinosaurs evolved various methods to maintain their body temperatures in different environments. During warmer periods, many large dinosaurs likely employed gigantothermy, a strategy where their massive body size helped them retain heat. This allowed them to maintain a relatively stable internal temperature without the need for constant energy expenditure. Smaller dinosaurs, on the other hand, may have relied more on behavioral adaptations, such as seeking shade or basking in the sun to regulate their body heat. In cooler climates, some dinosaurs developed specialized features to conserve heat. Feathers, which were initially thought to be limited to avian dinosaurs, have been discovered on various non-avian species as well. These feathers likely served as insulation, helping dinosaurs retain body heat in colder environments. Additionally, some dinosaurs may have migrated seasonally to avoid extreme temperatures, much like modern birds and mammals do today. The diversity of dinosaur thermoregulation strategies highlights their remarkable adaptability to changing climatic conditions. This ability to regulate body temperature effectively in various environments was likely a key factor in their dominance for over 160 million years, allowing them to thrive in a wide range of habitats across the globe. Dinosaur bones hold clues about how these ancient creatures regulated their body temperature. By examining the microscopic structure of fossilized bones, scientists can gain insights into dinosaur metabolism and growth rates. This information helps determine whether dinosaurs were cold-blooded like modern reptiles or warm-blooded like birds and mammals. One key feature scientists look for in dinosaur bones is called lines of arrested growth. These are similar to tree rings and indicate periods of slower growth, often due to seasonal changes or limited resources. The presence and frequency of these lines can suggest whether a dinosaur had a constant growth rate like warm-blooded animals or a more variable one like cold-blooded creatures. Another important aspect of bone structure is the density of blood vessels. Warm-blooded animals typically have more blood vessels in their bones to support their higher metabolic rates. By studying the tiny holes left by blood vessels in fossilized dinosaur bones, researchers can estimate how energy-demanding their lifestyles were. The balance of different bone tissues, such as dense cortical bone and spongy trabecular bone, also provides clues about dinosaur thermoregulation. This balance varies between warm and cold-blooded animals, helping scientists piece together the metabolic puzzle of these long-extinct creatures. Through careful analysis of these bone features, paleontologists continue to refine our understanding of dinosaur physiology and behavior. Thermoregulation strategies in dinosaurs were diverse and fascinating, varying significantly between small and large species. Smaller dinosaurs, with their higher surface area to volume ratio, faced different challenges compared to their larger counterparts. For smaller dinosaurs, maintaining body heat was a primary concern. Many likely employed strategies similar to modern small mammals and birds. These may have included behavioral adaptations, such as seeking sunny spots to bask, huddling together for warmth, and possibly even some form of insulation like protofeathers or downy coverings. Some small dinosaurs might have been endothermic, generating their own body heat through metabolic processes, allowing them to remain active in cooler environments. In contrast, large dinosaurs had the opposite problem, avoiding overheating. Their massive bodies retained heat efficiently, potentially to the point of excess. To combat this, they likely used methods similar to modern large animals like elephants. This could have included behavioral cooling strategies, such as seeking shade or wallowing in water. Some may have had specialized blood vessel structures near the skin surface to help dissipate heat, similar to the ears of modern elephants. Additionally, their large size meant they cooled down and warmed up slowly, a phenomenon known as gigantothermy, which helped maintain a stable body temperature. Interestingly, medium-sized dinosaurs might have employed a mix of these strategies, adapting their thermoregulation methods based on environmental conditions. This range of thermoregulation strategies across different dinosaur sizes showcases the remarkable adaptability of these ancient creatures to their varied environments. Dinosaurs roamed the Earth for over 160 million years, adapting to a wide range of environments and climates. While many dinosaurs thrived in warm, tropical conditions, some species evolved to survive in more extreme temperatures. In colder regions, particularly at high latitudes, scientists have discovered fossils of dinosaurs that appear to have been well adapted to chilly conditions. One notable example is the Cryolophosaurus, a large carnivorous dinosaur that lived in Antarctica during the early Jurassic period. This dinosaur likely had features that helped it withstand the cold, such as a higher metabolism and possibly even some form of insulation. On the other end of the spectrum, dinosaurs also adapted to extremely hot environments. The Sahara Desert was once home to numerous dinosaur species, including the massive Spinosaurus. This large predator had unique adaptations that allowed it to thrive in a hot, semi-aquatic environment, such as dense bones for buoyancy and a sail-like structure on its back that may have helped with thermoregulation. These examples demonstrate the remarkable adaptability of dinosaurs, showcasing their ability to evolve and thrive in diverse climates across the globe. From the icy regions of ancient Antarctica to the scorching deserts of North Africa, dinosaurs found ways to survive and flourish in extreme conditions. Thermoregulation played a crucial role in shaping the activity patterns of dinosaurs, influencing when and how they moved, hunted, and rested. Unlike modern mammals and birds, most dinosaurs were likely mesotherms, occupying a middle ground between cold-blooded and warm-blooded animals. This unique metabolic strategy allowed them to be active for longer periods than purely cold-blooded creatures, but also required careful management of their body temperature. During the hottest parts of the day, large dinosaurs may have sought shade or wallowed in water to prevent overheating. Their massive bodies retained heat efficiently, which was advantageous in cooler temperatures but problematic in extreme heat. Smaller dinosaurs, with their higher surface area to volume ratio, could have been more active during these peak temperature hours, taking advantage of their ability to shed excess heat more easily. As temperatures cooled in the evening and early morning, larger dinosaurs likely became more active. These periods would have been ideal for hunting, foraging, and other energy-intensive activities. The retained body heat from the day would have allowed them to remain active even as the environment cooled, giving them an edge over smaller, more temperature-dependent prey. The need for thermoregulation also influenced dinosaur behavior across seasons. During colder months, dinosaurs may have engaged in activities to warm up, such as basking in the sun or huddling together. Some species might have migrated to warmer climates or hibernated to conserve energy when food was scarce. This delicate balance of heat management shaped not only daily routines, but also broader patterns of dinosaur behavior and distribution across different environments and time periods. Birds and crocodiles offer valuable insights into dinosaur thermoregulation, providing scientists with living models to study. As the closest living relatives of dinosaurs, birds descended from a group of theropod dinosaurs, while crocodiles share a common ancestor with dinosaurs from the Archosaur lineage. Birds, being warm-blooded, showcase highly efficient thermoregulation systems. Their unique respiratory system, featuring air sacs and one-way airflow through the lungs, allows for effective heat exchange. This advanced system likely evolved from their dinosaur ancestors, suggesting that at least some dinosaurs may have had similar thermoregulatory capabilities. Crocodiles, on the other hand, are ectothermic, but can regulate their body temperature through behavioral means. They bask in the sun to warm up and seek water to cool down. Some scientists propose that certain dinosaur species might have employed similar strategies, especially larger ones that could maintain a stable body temperature through thermal inertia. By studying the physiological and anatomical features of both birds and crocodiles, researchers can piece together a more comprehensive understanding of how dinosaurs might have regulated their body temperature. This comparative approach helps scientists reconstruct the evolutionary path of thermoregulation from ancient archosaurs to modern birds, shedding light on the diverse strategies dinosaurs may have used to maintain optimal body temperatures in various environments. Dinosaurs possessed a diverse array of sensory capabilities that varied across different species. Their senses were often highly adapted to their specific environments and lifestyles. Vision was particularly well developed in many dinosaur species. Large, predatory dinosaurs like Tyrannosaurus rex had forward-facing eyes that provided excellent depth perception, crucial for hunting. Some herbivorous dinosaurs, such as Triceratops, had eyes positioned on the sides of their heads, offering a wide field of view to detect potential predators. The sense of smell was acute in many dinosaurs, especially among the theropods. Tyrannosaurus rex, for instance, had an exceptionally large olfactory bulb, suggesting a keen sense of smell that may have rivaled or surpassed that of modern-day bloodhounds. This powerful olfactory ability would have been invaluable for tracking prey over long distances. Hearing abilities varied among dinosaur species. Some, like the duck-billed hadrosaurs, had complex inner ear structures that suggest they could perceive a wide range of sounds, possibly using low-frequency calls for communication. Others, like certain sauropods, may have been more limited in their hearing range. While it is challenging to determine the exact acuity of dinosaur senses, Fossil evidence and comparisons with modern relatives provide valuable insights into their sensory world, revealing a complex and varied picture of how these ancient creatures perceived and interacted with their environment. Dinosaur skull structure provides valuable insights into their sensory capabilities, offering a window into how these ancient creatures perceived and interacted with their environment. The size and shape of eye sockets in dinosaur skulls give clues about their visual acuity and depth perception. Large, forward-facing eye sockets suggest predatory dinosaurs had excellent binocular vision, crucial for hunting and judging distances accurately. Nasal cavities and olfactory bulbs in dinosaur skulls reveal information about their sense of smell. Some dinosaurs, like Tyrannosaurus rex, had large olfactory bulbs, indicating a highly developed sense of smell that likely aided in locating prey or carrion over long distances. The structure of the inner ear, preserved in some well-fossilized skulls, offers clues about hearing capabilities and balance. Skull features also provide evidence of specialized sensory organs. For instance, the presence of small pits and grooves on the snouts of some dinosaurs suggests they had pressure-sensitive receptors, similar to those found in modern crocodiles. These receptors may have helped aquatic or semi-aquatic dinosaurs detect movement in water, aiding in prey location or navigation. The shape and arrangement of teeth in dinosaur skulls not only indicate diet, but can also suggest the presence of specialized sensory structures. Some herbivorous dinosaurs had complex tooth batteries that may have contained nerve endings, allowing them to sense the texture and composition of the plants they ate. This sensory information would have been crucial for efficient foraging and avoiding potentially harmful vegetation. Dinosaur vision was remarkably advanced, rivaling and in some cases surpassing that of modern animals. Many dinosaurs possessed large eyes relative to their skull size, suggesting vision played a crucial role in their daily lives. This was particularly true for predatory species like Tyrannosaurus rex, whose eyes were comparable in size to those of modern-day eagles. Evidence from fossilized eye sockets and related bone structures indicates that many dinosaurs had excellent depth perception. This binocular vision would have been invaluable for hunting or navigating complex environments. Some scientists believe certain dinosaurs may have had visual acuity up to 6 times sharper than humans, allowing them to spot prey or predators from great distances. Interestingly, many dinosaurs likely possessed tetrachromatic vision, meaning they could see 4 primary colors instead of the 3 that most humans perceive. This additional color receptor, still found in modern birds and reptiles, would have allowed dinosaurs to distinguish between a broader range of colors, potentially aiding in everything from finding food to selecting mates. However, not all dinosaurs had superior vision. Some species, particularly those that lived in low-light environments or relied more heavily on other senses, may have had less developed eyesight. Nonetheless, the overall picture that emerges is one of a group of animals that, in many cases, could see their world with remarkable clarity and detail, rivaling or exceeding the visual capabilities of many animals alive today. Many dinosaurs were indeed nocturnal, active during the dark hours when most of their contemporaries slept. This revelation challenges the long-held assumption that dinosaurs were primarily daytime creatures. Recent studies of fossil eye sockets have provided compelling evidence for nighttime activity in various dinosaur species. Scientists have examined the size and shape of the scleral ring, a bony structure in the eye, to determine the light-gathering ability of dinosaur eyes. Large eyes with wide pupils, similar to those of modern nocturnal animals, were found in several dinosaur species. This adaptation allowed them to see well in low-light conditions, suggesting they were well-suited for nighttime activities. Some of the dinosaurs believed to have been nocturnal include small carnivores like Velociraptor and herbivores such as Protoceratops. These nighttime hunters and foragers likely evolved their nocturnal habits to avoid competition with larger, diurnal predators, or to take advantage of different food sources available at night. The discovery of nocturnal dinosaurs adds a new dimension to our understanding of prehistoric ecosystems. It suggests a complex, round-the-clock world where different species occupied various temporal niches, much like in modern ecosystems. This diversity in activity patterns likely played a crucial role in the success and longevity of dinosaurs as a group. Dinosaur hearing capabilities varied significantly across different species, reflecting their diverse lifestyles and environments. Large sauropods, like Brachiosaurus, likely had limited hearing ranges focused on low-frequency sounds. Their massive size and long necks created challenges for detecting high-pitched noises, but they could potentially sense vibrations through the ground. In contrast, smaller theropods such as Velociraptor possessed more advanced hearing abilities. Their ear structures suggest they could detect a wider range of frequencies, including higher pitches. This enhanced hearing would have been crucial for hunting and avoiding predators in densely forested areas. Ceratopsians, like Triceratops, had unique hearing adaptations. Their large, frilled heads may have acted as sound-localizing devices, helping them pinpoint the direction of sounds. This could have been particularly useful for herd communication and predator detection on open plains. Some dinosaurs, such as the duck-billed hadrosaurs, had intricate nasal passages that possibly allowed them to produce and hear low-frequency sounds for long-distance communication. This adaptation would have been advantageous for maintaining contact within large herds across vast distances. Smell played a crucial role in dinosaur behavior, influencing many aspects of their daily lives. Like modern animals, dinosaurs used their sense of smell for various purposes, including finding food, detecting predators, and communicating with other members of their species. For carnivorous dinosaurs, a keen sense of smell was essential for hunting. Large predators like Tyrannosaurus rex likely had an excellent olfactory system, allowing them to track prey over long distances. This ability would have been particularly useful for detecting carrion, as the scent of decaying flesh could travel far and wide. Herbivorous dinosaurs also relied on their sense of smell to locate suitable food sources and avoid toxic plants. Additionally, smell was likely important for social interactions among dinosaurs. Many species may have used scent markers to establish territories or communicate with potential mates, similar to how modern animals use pheromones. Recent fossil evidence suggests that some dinosaurs had highly developed olfactory bulbs in their brains, indicating an advanced sense of smell. This adaptation would have been particularly valuable for navigating complex environments, avoiding danger, and surviving in the diverse ecosystems of the Mesozoic era. While many dinosaurs had keen senses similar to modern animals, some possessed truly remarkable sensory abilities. The Spinosaurus, a massive predatory dinosaur that lived during the Cretaceous period, might have had electroreception capabilities similar to those found in sharks and platypuses today. This potential ability would have allowed Spinosaurus to detect the electrical impulses of prey hiding in murky waters, giving it a significant advantage as a semi-aquatic hunter. Another dinosaur with an unusual sensory adaptation was the Nigersaurus, a sauropod with a wide, straight-edged muzzle filled with hundreds of teeth. Some paleontologists believe this dinosaur may have had pressure-sensitive organs in its snout, allowing it to detect subtle changes in its environment and locate food more efficiently. The Therizinosaurus, known for its enormous claws, might have possessed highly sensitive nerve endings in its hands. This heightened tactile sense could have helped it forage for food and navigate its surroundings more effectively. Additionally, some scientists speculate that certain dinosaurs, particularly those with elaborate head crests like Parasaurolophus, might have used these structures for enhanced hearing or even echolocation. While much of what we know about dinosaur senses remains speculative, ongoing research and new fossil discoveries continue to reveal fascinating insights into the sensory world of these ancient creatures. The possibility of unusual senses in dinosaurs highlights the diverse adaptations that evolved over millions of years, allowing these remarkable animals to thrive in their prehistoric environments. Dinosaurs relied heavily on their sensory abilities to hunt and forage effectively. Their keen senses played a crucial role in their survival and success as dominant terrestrial animals for over 160 million years. For predatory dinosaurs, vision was often a primary tool. Many theropods, like Tyrannosaurus rex, had forward-facing eyes that provided excellent depth perception, crucial for judging distances when pursuing prey. Some dinosaurs also possessed large eyes relative to their skull size, suggesting they may have been adept at hunting in low-light conditions. Smell was another vital sense for both carnivorous and herbivorous dinosaurs. Olfactory bulbs in the brains of some species were well developed, indicating a strong sense of smell. This would have allowed predators to track prey over long distances and helped herbivores locate suitable vegetation or detect the presence of nearby carnivores. Hearing also played a significant role in dinosaur survival strategies. Some dinosaurs, such as the duck-billed hadrosaurs, had complex inner ear structures that suggest they could detect a wide range of sounds. This ability would have been useful for communication within herds and for early warning of approaching predators. For carnivores, acute hearing would have aided in locating prey and coordinating pack hunting behaviors. The size and shape of dinosaur nostrils provide fascinating insights into their olfactory abilities. Paleontologists have long studied fossilized skull remains to understand how well different dinosaur species could smell. Larger nasal openings often indicate a more developed sense of smell as they allow for a greater surface area of olfactory receptors. Tyrannosaurs, for example, had particularly large nasal cavities, suggesting they possessed an acute sense of smell. This powerful olfactory ability likely aided in hunting and detecting prey from considerable distances. In contrast, some herbivorous dinosaurs like Stegosaurus had smaller nasal openings, indicating a less developed sense of smell, which aligns with their plant-based diet, requiring less scent detection for survival. The shape of nasal passages also plays a crucial role. Some dinosaurs had complex, winding nasal passages that increased the surface area for scent detection. This intricate structure allowed for better air filtration and scent processing, enhancing their overall olfactory capabilities. Recent studies have even suggested that some dinosaurs might have had vomeronasal organs similar to those found in modern reptiles and mammals. These organs, dedicated to detecting pheromones, would have played a significant role in social behaviors, mating, and territory marking. While direct evidence of these organs is difficult to find in fossils, the nasal structure of certain dinosaur species hints at their possible existence. Dinosaur sensory abilities underwent significant changes throughout their long evolutionary history. Early dinosaurs likely had basic senses similar to their reptilian ancestors, but as they diversified and adapted to various environments, their sensory capabilities became more sophisticated. Vision saw remarkable improvements in many dinosaur lineages. Some predatory dinosaurs evolved forward-facing eyes, enhancing their depth perception and ability to track prey. Herbivorous species often developed eyes positioned on the sides of their heads, providing a wider field of view to detect potential threats. The size of eye sockets in fossil records suggests that many dinosaurs had excellent vision, with some possibly possessing night vision capabilities. Hearing also evolved substantially. The structure of the inner ear in various dinosaur fossils indicates that many species could detect a wide range of frequencies. Some dinosaurs, particularly in the theropod group, developed enlarged cochlea, suggesting enhanced hearing abilities. This would have been crucial for communication, hunting, and avoiding predators. The sense of smell saw significant advancements in certain dinosaur groups. Tyrannosaurus rex, for instance, had an exceptionally large olfactory bulb, indicating a highly developed sense of smell. This would have aided in locating prey, even from considerable distances. Herbivorous dinosaurs also benefited from improved olfaction, helping them identify suitable food sources and detect potential dangers. Dinosaurs, like all living creatures, were susceptible to a variety of diseases and health issues. paleontologists have uncovered evidence of several ailments that plagued these ancient reptiles. One common problem was bone infections, which left telltale marks on fossilized remains. These infections could cause severe pain and limit mobility, potentially leading to death if left untreated. Arthritis was another condition that affected dinosaurs, particularly in older individuals. Fossil evidence shows joint inflammation and bone spurs, indicating that some dinosaurs lived with chronic pain. Tooth decay has also been observed in dinosaur fossils, suggesting that even these prehistoric giants were not immune to dental problems. Parasitic infections were likely widespread among dinosaurs. Fossilized feces, known as coprolites, have revealed the presence of intestinal parasites similar to those found in modern animals. These parasites could have caused malnutrition, weakness, and other health complications. Additionally, scientists have discovered evidence of tumor-like growths in some dinosaur bones, indicating that cancer may have affected these ancient creatures as well. Respiratory infections, similar to pneumonia, might have been common, especially among herbivorous dinosaurs that lived in herds. Close contact between individuals could have facilitated the spread of such diseases. While our understanding of dinosaur diseases is limited by the fossil record, these findings offer fascinating insights into the health challenges faced by these remarkable animals millions of years ago. Paleontologists employ several sophisticated techniques to identify diseases in dinosaur fossils. One key method involves carefully examining bone structure for abnormalities. Diseases often leave distinct marks or alterations in bones, which can be detected even millions of years later. For instance, arthritis might cause visible joint deformities, while bone cancer could create unusual growths or lesions. Advanced imaging technologies play a crucial role in this process. Computed tomography scans allow scientists to peer inside fossilized bones without damaging them, revealing internal structures and potential signs of illness. These scans can detect minute changes in bone density or composition that might indicate past infections or other health issues. Microscopic analysis of fossil samples also provides valuable insights. By studying thin sections of bone under powerful microscopes, paleontologists can observe cellular-level changes that might be associated with specific diseases. This technique has helped identify conditions such as osteomyelitis, a type of bone infection in dinosaur remains. Comparisons with modern animals further aid in disease identification. Many illnesses affecting dinosaurs have counterparts in their living relatives, such as birds and reptiles. By understanding how these diseases manifest in contemporary species, scientists can make informed inferences about similar conditions in prehistoric creatures. This multifaceted approach allows paleontologists to unravel the health challenges faced by dinosaurs millions of years ago, providing a more complete picture of their lives and ecosystems. Dinosaurs, like all living creatures, were susceptible to various diseases and infections. While we cannot directly observe dinosaur-specific pathogens, paleontologists and researchers have found evidence of illnesses and infections in fossilized dinosaur remains. One notable example is a condition similar to modern-day trichomoniasis, a parasitic disease that affects birds. Fossils of Tyrannosaurus rex have shown lesions in their jaws that resemble those caused by this infection. This suggests that dinosaurs may have suffered from similar parasitic diseases. Another potential dinosaur-specific pathogen is evidenced by fossilized tumors found in hadrosaur bones. These tumors, which resemble modern-day cancerous growths, indicate that dinosaurs were vulnerable to certain types of cancer or tumor-causing pathogens. Fossilized dinosaur feces, known as coprolites, have also provided insights into potential parasitic infections. Researchers have found evidence of parasitic worm eggs in some coprolites, suggesting that intestinal parasites were present in dinosaur populations. While we cannot definitively identify specific pathogens, these findings offer glimpses into the health challenges faced by dinosaurs millions of years ago. Diseases likely played a significant role in shaping dinosaur populations and evolution, much as they do for modern animals. Paleontologists have found evidence of various ailments in fossilized dinosaur remains, including bone infections, arthritis, and even cancer. These discoveries suggest that dinosaurs were susceptible to a wide range of health issues that could have influenced their survival and reproductive success. One particularly intriguing example is the presence of tiny holes in some fossilized bones, which researchers believe may have been caused by parasites. These parasites could have weakened individual dinosaurs, making them more vulnerable to predators or less able to compete for resources. Over time, such infestations might have led to evolutionary adaptations in dinosaur immune systems or behaviors to combat these threats. Viral and bacterial infections probably also impacted dinosaur populations, potentially causing widespread die-offs similar to those observed in modern ecosystems. Such events could have created evolutionary pressures, favoring individuals with stronger immune responses or physical traits that made them less susceptible to certain pathogens. This process may have contributed to the diversity of dinosaur species we see in the fossil record. It is important to note that studying diseases in extinct animals presents significant challenges, as soft tissues rarely fossilize. However, by examining bone abnormalities and comparing them to modern animal diseases, scientists continue to uncover new insights into the health challenges faced by these ancient creatures and how those challenges shaped their evolution over millions of years. Bone abnormalities in dinosaur fossils provide a fascinating window into the health and lives of these ancient creatures. These skeletal clues offer paleontologists valuable insights into the diseases, injuries, and overall well-being of dinosaurs that lived millions of years ago. One common type of bone abnormality found in dinosaur remains is evidence of fractures and breaks. These injuries can reveal information about the hazards dinosaurs faced in their environments and their ability to survive traumatic events. For instance, healed fractures indicate that some dinosaurs were able to recover from serious injuries, suggesting they had robust immune systems and possibly received care from their social groups. Arthritis and joint diseases are also frequently observed in dinosaur fossils. These conditions can tell us about the physical stresses dinosaurs endured, their longevity, and how their bodies coped with aging. Additionally, abnormal bone growths or tumors found in some specimens provide evidence of various forms of cancer and other diseases that affected these prehistoric animals. Studying these bone abnormalities not only sheds light on individual dinosaur health, but also helps scientists understand broader aspects of dinosaur biology, behavior, and evolution. By comparing the frequency and types of abnormalities across different species and time periods, researchers can gain insights into how dinosaurs adapted to changing environments and the health challenges they faced throughout their long reign on Earth. While we cannot definitively say there were pandemic-like events among dinosaurs, evidence suggests that ancient animals, including dinosaurs, likely experienced widespread diseases. Fossilized bones have revealed signs of infections and illnesses that could have spread through populations. One intriguing example comes from hadrosaurs, duck-billed dinosaurs that lived in herds. Paleontologists have discovered numerous hadrosaur fossils with similar abnormalities in their bones, indicating a common ailment that affected multiple individuals. This could be evidence of a disease that spread through their communities, much like a modern pandemic. Another potential case involves theropod dinosaurs, the group that includes Tyrannosaurus rex. Some fossils show signs of a condition similar to trichomoniasis, a disease that affects modern birds. If this disease was present in ancient theropods, it could have spread rapidly among populations, especially if they lived in close proximity or shared feeding grounds. It is important to note that the fossil record provides only glimpses into the lives and deaths of dinosaurs. Many diseases leave no trace on bones, making it challenging to identify prehistoric pandemics conclusively. However, given the long history of life on Earth and the prevalence of diseases in modern ecosystems, it is likely that dinosaurs faced their own versions of widespread illnesses throughout their reign. Parasites played a significant role in the lives of dinosaurs, much as they do for modern animals. These ancient creatures were not immune to the effects of parasitic organisms, which likely influenced their health, behavior, and even evolution. Evidence from fossilized dinosaur remains has provided insights into the types of parasites that plagued these prehistoric giants. One of the most intriguing discoveries has been the presence of blood-sucking insects preserved in amber, dating back to the time of dinosaurs. These insects, similar to modern mosquitoes and ticks, would have fed on dinosaur blood, potentially spreading diseases and causing discomfort. Larger external parasites, akin to today's fleas and lice, probably infested the feathers and scales of various dinosaur species. Internal parasites also affected dinosaurs. Coprolites, or fossilized feces, have revealed the presence of intestinal worms in some dinosaur species. These parasites would have competed for nutrients, potentially weakening their hosts and making them more susceptible to other health issues or predation. Some scientists speculate that heavy parasite loads might have contributed to the decline of certain dinosaur populations over time. The relationship between dinosaurs and their parasites likely drove evolutionary adaptations on both sides. Dinosaurs may have developed behaviors or physical traits to combat parasites, while the parasites themselves would have evolved to better exploit their hosts. This ongoing battle between host and parasite continues to shape the natural world today, offering a fascinating link between the age of dinosaurs and our modern ecosystem. While we cannot directly observe dinosaur diseases, paleontologists and veterinary scientists have found evidence of ailments in fossilized dinosaur remains that bear similarities to modern animal diseases. Bone infections, for instance, appear to have been common among dinosaurs, much like they are in present-day reptiles and birds. These infections can lead to conditions such as osteomyelitis, which causes inflammation and deterioration of bone tissue. Arthritis, a condition affecting joints, has been identified in dinosaur fossils and is widespread among modern animals, including birds, which are considered living dinosaurs. This suggests that joint-related issues have persisted across millions of years of evolution. Similarly, evidence of gout, a form of inflammatory arthritis, has been found in dinosaur fossils, mirroring its occurrence in modern birds and reptiles. Respiratory infections, which can be devastating in modern animal populations, may have also plagued dinosaurs. Paleontologists have discovered signs of air sac infections in fossilized bones, reminiscent of pneumonia or air saculitis in contemporary birds. These respiratory issues could have been equally problematic for dinosaurs, given their similar respiratory systems. Cancer, a disease that affects virtually all complex life forms today, has also been identified in dinosaur fossils. Specifically, osteosarcoma, a type of bone cancer, has been observed in fossilized dinosaur bones, indicating that even these ancient creatures were not immune to cellular mutations and uncontrolled growth. This discovery underscores the long evolutionary history of cancer and its presence across diverse animal groups. Dinosaur immune systems, while not directly observable, likely shared many similarities with those of modern reptiles and birds. Scientists have pieced together clues from fossilized remains and comparisons with living relatives to form a picture of how these ancient creatures fought off disease. Like modern animals, dinosaurs almost certainly had both innate and adaptive immune responses. The innate immune system, the first line of defense against pathogens, probably included physical barriers like tough, scaly skin and chemical defenses such as antimicrobial proteins. Dinosaurs likely also had specialized white blood cells capable of engulfing and destroying invading microorganisms. The adaptive immune system, which develops specific responses to pathogens, was likely present in dinosaurs as well. This system, found in all modern vertebrates, would have allowed dinosaurs to produce antibodies tailored to fight specific infections. Evidence for this comes from the discovery of hollow channels in dinosaur bones, similar to those that house bone marrow in modern animals. Bone marrow is crucial for producing immune cells. One intriguing difference might lie in dinosaurs' ability to heal from injuries. Some fossil evidence suggests that dinosaurs could recover from severe wounds and bone fractures that would be life-threatening to many modern animals. This resilience might indicate a particularly robust immune response, possibly adapted to the harsh environments and frequent injuries these ancient reptiles faced in their daily lives. Diseases likely played a significant role in dinosaur extinctions, though their exact impact remains a subject of ongoing research and debate among paleontologists. While the Cretaceous-Paleogene extinction event, marked by a massive asteroid impact, is widely accepted as the primary cause of dinosaur extinction, diseases could have contributed to population declines and vulnerabilities leading up to this catastrophic event. Fossil evidence suggests that dinosaurs suffered from various ailments, including bacterial infections, parasitic infestations, and bone diseases. These health issues could have weakened dinosaur populations over time, making them more susceptible to environmental stresses and less resilient in the face of catastrophic events. One intriguing hypothesis proposes that changes in climate and vegetation during the late Cretaceous period might have altered the balance between dinosaurs and disease-carrying insects. As environments shifted, new interactions between dinosaurs and pathogens could have emerged, potentially leading to the spread of novel diseases that dinosaur immune systems were ill-equipped to handle. Furthermore, the stress caused by environmental changes and resource competition could have compromised dinosaur immune systems, making them more vulnerable to infections. This combination of factors might have created a perfect storm of disease susceptibility, contributing to gradual population declines and reduced genetic diversity among dinosaur species in the lead-up to their ultimate extinction. The distribution of dinosaur species across different regions was influenced by several factors, including continental drift, climate variations, and natural barriers. As the supercontinent Pangaea began to break apart about 200 million years ago, dinosaur populations became increasingly isolated. This separation allowed distinct species to evolve in different areas, adapting to their specific environments. Climate played a crucial role in determining where certain dinosaur species could thrive. Some dinosaurs were better suited to warm, tropical climates, while others adapted to cooler, more temperate regions. The availability of food sources in different areas also shaped dinosaur distribution, as herbivores would congregate where vegetation was abundant and carnivores would follow their prey. Natural barriers such as mountain ranges, deserts, and bodies of water further limited the movement of dinosaur species between regions. These obstacles prevented certain dinosaurs from spreading to new areas, leading to localized species development. Additionally, competition between different dinosaur species could restrict their range, with dominant species pushing others into specific niches or territories. Fossil evidence has revealed distinct dinosaur communities in various parts of the world. For example, the tyrannosaurs were primarily found in North America and Asia, while the spinosaurids were more common in Africa and Europe. This regional specificity in dinosaur distribution provides valuable insights into the complex interplay of geography, climate, and evolution during the Mesozoic era. Continental drift played a crucial role in shaping the distribution of dinosaurs across the planet. When dinosaurs first appeared around 230 million years ago, Earth's landmasses were united in a supercontinent called Pangaea. This vast landmass allowed dinosaurs to roam freely, leading to similar species evolving across wide areas. As Pangaea began to break apart about 180 million years ago, dinosaur populations became increasingly isolated. This separation led to the evolution of distinct species on different continents. For example, the split between South America and Africa resulted in unique dinosaur lineages developing on each continent. The movement of continents also created new environmental conditions influencing dinosaur evolution. As land masses shifted, they encountered different climates and formed new mountain ranges and valleys. These changes prompted dinosaurs to adapt to their new surroundings, leading to a diverse array of species across the globe. Fossil evidence reflects this continental separation. We find different dinosaur species in North America compared to Europe or Asia, and unique forms in the southern continents of South America, Africa, and Australia. This distribution pattern provides valuable insights into both dinosaur evolution and the geological history of our planet. Throughout the age of dinosaurs, many species evolved and thrived in specific environments. However, some dinosaur species did achieve a remarkably widespread distribution across the ancient supercontinent of Pangaea. One of the most cosmopolitan dinosaurs was Allosaurus, a large carnivorous theropod that lived during the late Jurassic period. Fossils of Allosaurus have been found across North America, Europe, and Africa, indicating its ability to adapt to various environments and climates. This widespread distribution suggests that Allosaurus was a highly successful predator capable of thriving in diverse ecosystems. Another example is Diplodocus, a long-necked sauropod dinosaur. Remains of Diplodocus and closely related species have been discovered in North America, Europe, and parts of Africa. This extensive range demonstrates the adaptability of these massive herbivores to different habitats and food sources across continents. The ceratopsian dinosaur, Psittacosaurus, also showed a wide distribution, with fossils found across much of Asia, from Siberia to China, and possibly as far as Thailand. While not as globally widespread as some other species, Psittacosaurus exemplifies how certain dinosaurs could thrive across vast geographical areas within a single continent. Climate played a crucial role in shaping the geographic distribution of dinosaurs throughout their reign on Earth. These ancient reptiles inhabited our planet for over 160 million years, during which time they experienced significant climatic changes that influenced their habitats and migration patterns. During the Mesozoic era, when dinosaurs thrived, the Earth's climate was generally warmer and more humid than it is today. This allowed many dinosaur species to spread across vast areas, including regions that are now covered in ice. As the continents shifted and the global climate fluctuated, dinosaurs adapted and moved to new territories that suited their needs. The distribution of vegetation, which was directly impacted by climate, was a key factor in dinosaur distribution. Herbivorous dinosaurs followed the plant life they depended on for food, while carnivorous species tracked their prey. As climate changes caused shifts in plant communities, entire dinosaur ecosystems migrated to new areas. Fossil evidence suggests that some dinosaur species were better adapted to specific climates. For instance, large sauropods with their long necks were well suited to warm, lush environments with abundant vegetation, while smaller feathered dinosaurs could survive in cooler regions. This climate-driven specialization led to distinct dinosaur communities in different parts of the world, contributing to the incredible diversity of these prehistoric creatures. The fossil record provides invaluable insights into the geographic distribution of dinosaurs over time, revealing patterns of range expansion and contraction across millions of years. By examining fossils from different locations and geological periods, paleontologists can piece together a dynamic picture of how dinosaur populations moved and adapted to changing environments. One key revelation from the fossil record is the evidence of dinosaur migration and colonization of new territories. Fossils of similar species found on multiple continents suggest that dinosaurs were able to traverse vast distances, often by crossing land bridges that existed during certain periods. For instance, the discovery of closely related dinosaur species in both North America and Asia indicates that these animals likely moved between the two continents when they were connected. The fossil record also shows how dinosaur ranges contracted in response to environmental pressures. During periods of global cooling or other climatic shifts, fossils indicate that some dinosaur species retreated to more hospitable regions. This contraction of range is particularly evident in the late Cretaceous period, just before the mass extinction event that wiped out non-avian dinosaurs. Furthermore, the fossil record reveals how the rise and fall of sea levels influenced dinosaur distribution. As oceans receded, new land bridges formed, allowing dinosaurs to expand their territories. Conversely, rising sea levels could isolate populations, leading to the evolution of distinct species in different regions. This interplay between geography and evolution is clearly documented in the diverse array of dinosaur fossils found across the globe. Physical barriers played a crucial role in shaping dinosaur distribution across the ancient Earth. During the Mesozoic era, when dinosaurs roamed the planet, the continents were arranged differently than they are today. The supercontinent Pangaea began to break apart, creating new land masses and ocean basins. These geological changes formed natural barriers that influenced how dinosaur species spread and evolved. Mountain ranges, such as the early Rockies and Appalachians in North America, acted as formidable obstacles. These towering peaks limited the movement of certain dinosaur species, leading to isolated populations that developed unique characteristics over time. Similarly, expanding seas and newly formed oceans separated once connected lands, trapping dinosaur groups on different continents. Rivers and deserts also served as significant barriers. Wide, fast-flowing rivers could prevent larger dinosaurs from crossing, while vast, arid regions posed challenges for species not adapted to such harsh conditions. These obstacles led to the development of distinct dinosaur communities in different geographical areas, contributing to the rich diversity of species we observe in the fossil record. The impact of these physical barriers on dinosaur distribution helps explain why certain species were found only in specific regions. For instance, the Tyrannosaurus rex fossils have been discovered primarily in western North America, suggesting that geographical isolation played a part in its evolution and range. Understanding these ancient barriers provides valuable insights into the complex patterns of dinosaur evolution and biogeography throughout the Mesozoic era. Dinosaurs indeed inhabited islands during their long reign on Earth. Fossil evidence reveals unique species that evolved on isolated landmasses, adapting to their specific environments. One notable example is Europasaurus, a sauropod dinosaur that lived on an island in what is now northern Germany during the late Jurassic period, about 150 million years ago. Unlike its massive mainland relatives, Europasaurus was relatively small, standing only about 10 feet tall at the hip, a clear example of island dwarfism. Another fascinating island-dwelling dinosaur was Magearosaurus, discovered in Romania. This sauropod lived on an island archipelago in the Tethys Sea during the late Cretaceous period, roughly 70 million years ago. Like Europasaurus, Magearosaurus showed signs of insular dwarfism, being much smaller than its mainland counterparts. Islands also hosted carnivorous dinosaurs. Balor bondok, a peculiar predatory dinosaur found in Romania, lived on the same island archipelago as Magearosaurus. This unique carnivore had two large sickle-shaped claws on each foot, unlike its single-clawed mainland relatives. These island-dwelling dinosaurs provide valuable insights into evolutionary processes and how isolation can lead to distinct adaptations. Their existence demonstrates the diversity of dinosaur habitats and the species' ability to thrive in various environments, including small, isolated landmasses. Competition among dinosaur species played a crucial role in shaping their distribution across ancient landscapes. As different dinosaur groups evolved and diversified, they vied for resources such as food, water, and suitable habitats. This competitive pressure led to the development of specialized adaptations and influenced where various species could thrive. Herbivorous dinosaurs, for instance, often competed for plant resources. Some species developed long necks to reach vegetation at different heights, allowing them to coexist by exploiting distinct feeding niches. This adaptation enabled certain dinosaurs to spread into new territories where they could access food sources unavailable to their competitors. Carnivorous dinosaurs also faced intense competition, which affected their distribution. Larger predators often dominated prime hunting grounds. forcing smaller carnivores to adapt to different prey or seek out less contested areas. This competition drove some species to become more specialized hunters or to expand their ranges into previously unoccupied regions. The interplay of competition and adaptation led to a complex mosaic of dinosaur distributions across continents. Some species became widespread, while others remained localized in specific ecosystems where they had a competitive edge. This dynamic process continued throughout the age of dinosaurs, constantly reshaping the prehistoric world's biodiversity and geographic patterns. Migration played a crucial role in shaping dinosaur distribution patterns across the ancient world. As these remarkable creatures evolved and adapted over millions of years, they spread to new territories, driven by changing climates, shifting food sources, and the formation of land bridges between continents. During the Mesozoic era, when dinosaurs roamed the Earth, the continents were arranged differently than they are today. The supercontinent Pangaea began to break apart, creating new land masses and ocean basins. This continental drift opened up new migration routes for dinosaurs, allowing them to colonize previously inaccessible areas. Seasonal migrations were common among many dinosaur species, particularly herbivores. These animals would travel long distances in search of better feeding grounds as vegetation patterns changed with the seasons. Predatory dinosaurs often followed these migratory herds, leading to complex distribution patterns across vast landscapes. Fossil evidence suggests that some dinosaur species undertook intercontinental migrations. For example, similar dinosaur fossils found in both North America and Asia indicate that these animals crossed land bridges that existed between the continents during certain periods. These migrations contributed to the global spread of dinosaur species and influenced their evolution as they adapted to new environments. Recent fossil discoveries have dramatically altered our understanding of dinosaur distribution across ancient Earth. Paleontologists once believed certain dinosaur species were confined to specific continents, but new evidence reveals a more complex picture of their global spread. Fossils unearthed in Antarctica have shown that dinosaurs inhabited every continent, even in extreme environments. This challenges previous notions about their adaptability and range. Additionally, remains found in Africa and South America suggest that some species thought to be isolated actually had wider distributions than initially believed. Improved dating techniques have also refined our timeline of dinosaur evolution and migration. We now know that land bridges periodically connected continents, allowing dinosaurs to move between land masses that are separate today. This explains why similar species have been found on continents that were thought to be isolated during the age of dinosaurs. Perhaps most intriguingly, fossils of feathered dinosaurs, once considered unique to China, have now been discovered in North America and Europe. This suggests that feathered species were more widespread than previously thought, hinting at a global distribution of protobirds and changing our understanding of avian evolution.